Yeah, great. So welcome back, students. How are you all? It's been some long time since we have met. Last time I think we have met for maths one shot series on this channel, correct? So how many of you are ready to solve these questions of applied thermodynamics with me? So please type in the chat box. Yeah, good evening, Ismail, Prashant, Mayank, all of you. Yeah, Prashant here. Yeah, I hope correct. I remember you have called me sometimes. Okay. So previously I was on this channel. Yeah, good evening, all of you. Hi, Saiken. Yeah, good evening, Sukumar. Sorry. Yeah, Sukumar. Pradeep Kumar, hi. How are you? From Vizag. Okay, great. Vizag is always a beautiful city. A lot of fluid mechanics to talk about. We have a big sea and all. Okay, so good. So last time we met here for solving some Abhyas fluid mechanics questions. I have got a good response from you people. Actually, you have followed it very well. And then we have started recording this one-shot series of mathematics on this channel. Correct? How many of you have gone through this mathematics? I mean, I have done only for 3 chapters. But how many of you have gone through that one-shot series of mathematics? Thanks, Aiken. So please type in the chat box. How many of you have gone through that one shot series of mathematics actually that we have recorded? You have gone through. Great. Okay, so yeah, the main thing here is since GATE 2023 is very much approaching, okay, we have only few days left, almost some 20-25 days to the extent. So we have brought this revision to question series so that we can actually revise all the concepts and basic fundamentals by solving questions actually. Okay, because at the end of the day, when you are in the exam, how much subject you know is actually equivalent to how well you can solve the questions. Okay, even if your knowledge levels is a bit low, but still if you can solve the question, then it's good enough for that exam point of view. Okay, so here we have got some good, so I have put up some 15 good questions of applied thermodynamics. So we will discuss all these questions which are related to GATE mechanical syllabus and also to GATE XC syllabus a bit. Okay, because if you see syllabus, then GATE XC syllabus is a bit less as compared to GATE mechanical syllabus in terms of applied thermodynamics. Okay, so if you can solve these questions, then definitely that will help you in solving applied thermodynamics questions of GATE mechanical as well as GATE XC. Okay, so shall we start the questions? So shall we start these questions? And how many of you are following this RTQ regularly? Revision to question sessions, because daily we are solving some questions. Okay, like previously if you see, this is our team actually. So we have been solving these questions. Like for example, it started with basic thermodynamics. So we have done it on Thursday with by Negi sir, and then yesterday we have solved, I mean 14th by Apoop sir, we have solved these questions on engineering mathematics, and yesterday Vishal Soni sir has taken this mathematics sessions for you know, some good time. Okay, yes, let's start. Okay, great, fine. So and Swadesh sir has also taken this mechanical engineering, this basically manufacturing process and material science part 1 actually, and today we are going up with this applied thermodynamics. I myself will take that, and you have a long schedule waiting. So if you can follow this question series very well, and if you can focus thoroughly, then definitely you can get very good you know, knowledge in solving these questions of all these chapters, basically means all these subjects. Okay, so and we have Amulya sir for aptitude. So these two combinations, mathematics, of course I myself teach mathematics along with Vishal Soni sir, and aptitude, these two contribute to almost 30% of the total 100% marks of the GATE examination. Okay, so having some good knowledge in these two will definitely give you, they'll push you very much in qualifying the exam actually. Okay, so then we have some set of again core subjects, IE and OR by Amit Dikshit sir, again one of the very top notch faculties of this IE and OR. Then theory of machines and vibrations by Vishwajit sir, and manufacturing process 2 by one of my good friends and Aditya Paul sir actually. Then fluid mechanics and turbo machineries, while one of my colleagues will take this, Amit Moya sir, and again strength of metals by Apoop sir, and heat transfer by Sandeep sir. Okay, so we will actually go in a very much detailed way. You might have seen the previous sessions, those might have given you some good idea on how to you know, solve the questions and how to use the concepts in your questions, and in today's session we will put it more a step ahead in solving the questions of applied thermodynamics. Okay, and this is our most powerful and tremendous team. Like for example, you have a very good combination of all the people over here. Okay, so for example, coming to thermal discipline or thermal part, Negi sir, myself and Sandeep Chandrakar sir, and Amit Moya sir actually, we are taking care of this thermal module. And coming to the design module, we have this of course for mechanics we have Vinod Dasulia sir, and yeah, Vishwajit sir, Apoop sir, all these people. Similarly for IE and OR, we have the one of the best faculties of this GATE domain, like Swadesh Kumar Singh sir, then Aditya Paul sir, and Amit Dikshit sir for IE and OR, and all other machine design by Ramanand Bansal sir. We have a good, very good team actually. Okay, some of us have very good, great you know, exposure to the industries. Previously myself, I was working with Hindustan Petroleum and then later with BARC. Similarly, many of our team people have very good industrial touch, so that whenever we are discussing the concepts, we can give you the real-time examples. Okay. Similarly, in today's session also, I will talk about gas turbine power plants, which I used to work somewhere in HPCL. Okay. Normally, this intercooling, why we do this intercooling, all these things we will discuss on the go. Okay. So, are you all ready? So, shall we start these questions? So, shall we all start these questions? Are you all ready? Definitely, I have kept some questions which are matchable to gate level, but few questions I have kept something slightly more than the gate level. Okay, so let's start it. Great. Okay, so let's start the first question. So let us try to solve this question. A combustion ignition engine working on a standard diesel cycle has cylinder bore of 15 centimeters and stroke length is 25 centimeters. Clearance volume is 400 centimeter cube. The fuel injection takes place at constant pressure for 5% of the stroke. If the fuel supply continues up to 8% of the stroke, then the percentage loss in efficiency. So normally you might know this. Normally, if you go into engine details, especially for combustion ignition engines, CI engines, which generally work on diesel as the working fluid, so the cutoff is decided very, with very narrowness actually. Okay, if you see, the fuel cutoff should happen exactly at that particular point. If cutoff happens slightly prior, which you call early cutoff, and if cutoff even happens after a prescribed point, then definitely there is some fall in the efficiency of the cycle. Okay, so which we will see now. So here they have given you initially this cutoff is actually at 5% of the stroke at constant pressure, but now by increasing this cutoff to 8%, definitely there is some fall in the efficiency, thermal efficiency of the cycle. Okay, so they are asking you what is the loss in percentage. Okay, so the percentage loss in efficiency. So first of all, let us put an attempt to draw this A standard diesel cycle. Okay, so let us see. If you try to draw an A standard diesel cycle, I am putting it on a TS plot, temperature versus specific entropy plot. So T and S. Okay, so now we know the compression is isentropic compression here, 1 to 2. Then we go for a constant pressure heat addition. We go for a constant pressure heat addition in a diesel cycle. Okay, so 2 to 3, for example, this is a constant pressure heat addition. Then from here again we go for some isentropic expansion in the expansion cycle, and of course make sure when you are drawing this TS diagram, this point 4 is generally above this temperature 2. Okay, so because obviously it's common experience, when you see the exhaust gases, the exhaust is at higher temperature than the substance at the end of the combustion. Okay, so whenever you are drawing any TS plot, make sure the combustion gases temperature is generally higher than the temperatures after the combustion. Okay, so now this is 4, so you have again some isentropic compression, and obviously then you have this constant volume heat rejection. Okay, so this is 4 to 1. So if you write the process, constant volume, constant pressure, then isentropic process here, isentropic processes. Okay, now if you see carefully one thing here, the slopes of these two lines will be different. Look, this is a revision to questions. So when we are solving questions, it's not like we just try to put the solution to that question, but we will try to recollect different things. Okay, so on a TS plot, if you draw a constant pressure line and a constant volume line, definitely the constant volume line should have higher slope. Okay, the reason for this is the dt by ds on temperature versus entropy curve for constant volume is T by CV, and dt by ds of a constant pressure line is T by Cp, which you can easily see from your TDS equations. Okay, so whenever you try to try to draw a constant pressure line and a constant volume line on a TS diagram, you should always draw the constant volume line with higher slope. The reason being, whenever you see Cp is greater than Cv, so whenever Cp is greater than Cv, this quantity is low as compared to this quantity, so slope should be higher for constant volume line. Clear? So this has to be made a note. Anyhow, these are the two curves. Now let us see here. So they are asking you initially the cutoff is at 5% of the stroke. Okay, so let us take PV diagram also for your analysis. So PV also, for example, okay, because this could also help you in talking about volumes. So pressure and volume. Okay, now we have a combustion stroke. Let us say this is initial state of the volume. So we got a combustion stroke actually here till this point 2. Okay, then at constant pressure we do fuel supply. So at constant pressure we are doing fuel supply. So this is 3. So we are doing constant pressure fuel supply. Then we have a constant isentropic expansion again to state 4, and at constant volume heat rejection. Okay, so we have a constant volume heat rejection here. So here if you see in this cycle we have work input and work output in the expansion stroke, and also some partial work output in this case also. Okay, we have work output in this case as well. Then this is the stroke in which you are supplying the fuel, correct? Now let us see, let us take the data that's given to us. Now 1 2 3 4 and corresponding TS cycle. Okay, now if you see working on a standard cycle, the cylinder bore is 15 centimeters. Means if you have the piston, the diameter of the piston is actually 15 centimeters. So diameter is 15 centimeters, which is 0.15 meters, correct? Then and stroke length of 25 centimeters. So the piston can oscillate for a length of 25 centimeters. Okay, so this is 0.25 meters. Great. Now if you see the clearance volume is 400 centimeter cube. So clearance volume means in this case if you see practically what happens, the piston actually moves in between these two volumes, correct? So whenever the piston reaches here, this volume which is left is the clearance volume. So V2 I'm taking it as 400 centimeter cube. Okay, now this is 400 centimeter cube. Fuel injection is taking place at constant pressure for 5% of the stroke initially. Okay, so case 1, if you take case 1, fuel injection is taking place up to 5% of the stroke. What is the meaning of this? So if you see, fuel injection takes from this particular point to this particular point, correct? So all over the movement of this piston, fuel is actually injected into the cylinder, correct? So V3 minus V2, where this is the span of fuel injection, this is 5% of the stroke. What is the meaning of 5% of the stroke? Stroke is this total volume, correct? So therefore 5 by 100 times of V1 minus V2, correct? This is the meaning of cutoff happens at 5% of the stroke. Is this clear to all of you? Did you all understand how did I write this equation? This is cutoff means the volume up to which the movement of the piston during which the fuel is injected into the cylinder, and this is the total cylinder swept volume. Okay, so that's how V3 minus V2 is 5% of this particular value. Clear to all of you? So please type in the chat box, is this clear? Did you all understand how did I write this equation? V3 minus V2 is 5% of the total swept volume. Clear? Okay, now let us see. This implies if you divide with V2, V3 by V2, which is the cutoff ratio minus 1, is equal to 5 by 100 times of V1 by V2 minus 1. Now I will ask you one question, so please try to answer this. What is V1 by V2? Means if you take the ratio of volume at this location to volume at this location, what is V1 by V2 in this question? Or in general in any cycle, if you say for example in any A standard cycles, what is the ratio of V1 by V2? What is the ratio of V1 by V2? Yes, very good. It is nothing but compression ratio, correct? So yes, compression ratio. So this value is actually equal to the compression ratio R. But you don't know what is the compression ratio. They didn't give you in the question, correct? So how do you get the cutoff ratio here? So please tell me, they didn't give you the compression ratio in this question. Anyway, they didn't talk about the compression ratio. Then how do you identify what is the cutoff ratio? I mean, what is the compression ratio? How do you identify this? Look, we have the length of the piston movement and the diameter of this cylinder, correct? So if you can calculate the swept volume, then total volume available at the beginning of compression, which is nothing but V1, is nothing but V swept plus V clearance, correct? So we know R is equal to VT by VC. This V total can be written as V swept plus V clearance by V clearance. Okay, so clearance volume is given to you, which is 400 centimeter cube. Now what is swept volume? Swept volume is pi by 4 d square. Since this is in centimeter cube, let us put this in centimeters. 15 square into 25 plus 400 divided by 400, correct? This is what you have. Clear? So this gives you your compression ratio actually here. Okay, so compression ratio is calculated from this equation. So let us calculate this value. Let us take a calculator. 15 square into 25. Okay, so 15 square into 25 into pi by 4 into pi by 4. Okay, so into pi by 4, this value plus 400 plus 400. This is the total volume divided with 400 gives you 12.04. So normally for combustion ignition engines it is around 12. So 12.04. So this is how we can calculate the combustion ratio in this case. Okay. So R is equal to 12.04. Clear? So whenever R is equal to 12.04, so if you replace here, we get the cutoff ratio in this case. Rho minus 1 is equal to 5 by 100 times of this 12.04 minus 1 actually here. Okay. So from this we can calculate cutoff. Let us say this is the first case. So rho 1 is equal to, we get some value here. Okay. So let us get this value. Sorry, 2.128%. I think you're telling the final answer. Nikhil, is it? Are you telling the final answer? Are you telling the final answer, Nikhil? Let us see. Okay. By the time we reach the end, let us compare the answers. Okay. So now if you see this value, if you see 12.04, so this value minus 1 into 5 by 100, so 0.05. So this value plus 1. So cutoff ratio is 1.5522. 1.552 to 3 decimals if you take for example. Okay. So this is the cutoff ratio in the first case. Okay. Now let us talk about the second case. They have increased the cutoff from 5% to 8%. Correct. So here they are telling you that if the fuel supply continues up to 8% of the stock. So in second case, let us see what happens. Case 2. Case 2. V3 minus V2 or rho 2 directly I'm writing is equal to 1 plus 8 by 100 times of 12.04 minus 1. Correct. Because from this equation you might understand rho and combustion ratio are related by this equation. So here we are just increasing the cutoff to 8%. So that's why we have 8 here. Okay. So if you do this calculation, then rho 2 is equal to, what about rho 2? Let us see. Rho 2 is how much? 12.04 minus 1 into 0.08. So this is the value plus 1. Okay. So plus 1. 1.8832. 1.8832. Correct. So this is the cutoff ratio here. Now we know the cutoff ratio. This is a combustion ignition cycle, or generally combustion ignition engine works on a standard diesel cycle. Okay. So what could be the formula for the thermal efficiency? Let us see. If you take a slide for example. Fine. So let us see. Thermal efficiency of diesel cycle is equal to 1 minus 1 by R power gamma minus 1 into rho power gamma minus 1 by rho minus 1. Correct. This is what we have. Yes or no? So please type in the chat box. So all of you, please type in the chat box. Is this the formula for the thermal efficiency of a diesel cycle? Yes or no? Okay. Can you recollect this? So please type in the chat box. Can you all recollect this? Thermal efficiency of a diesel cycle is given by this, where R is the combustion ratio and rho is the cutoff and gamma is the adiabatic index of the substance. Correct? Yes or no? Right? Thermal efficiency is equal to 1 minus 1 by R power. Sorry? Okay, sorry. I think I missed gamma. Okay, fine. This gamma is also there. Correct. Gamma times of rho minus 1. Yes, correct. I think I missed gamma. So is this the correct formula? So please type in the chat box. There is also one gamma, correct? Okay. Yeah, gamma is missing in the denominator. Correct. I forgot to write gamma. So gamma times of rho minus 1. Correct. So now if you see in case 1, what are the parameters? What are the parameters here? R is 12.04. Cutoff ratio is how much? Cutoff is 1.552. And gamma of the substance, if you take air, it is 1.4 diatomic gas generally. So we can evaluate this expression. Okay. Similarly, in case 2, again combustion ratio is 12. This time we got, yes, 12.04. Combustion ratio is same. Cutoff ratio is 1.8832. And gamma is again 1.4. Okay. Now they are asking you percentage loss in efficiency. Okay. So they are asking you percentage loss, which is efficiency in case 1 minus efficiency in case 2 by efficiency of case 1 into 100%. Okay. So this is what they want actually. Okay. So once you calculate this, then things are done. Okay. So how to calculate this? Put the values. Thermal efficiency in first case is equal to 1 minus 1 by r power gamma minus 1, which is 0.4 times of rho power gamma. Rho is 1.552 whole power gamma minus 1 by gamma into rho minus 1 actually. Okay, so this is the value. So we'll get some value here. Similarly, thermal efficiency of second case is 1 minus 1 by 12.04 whole power gamma minus 1 times of 1 point. This cutoff ratio is 883 power 1.4 minus 1 by 1.4 times of 1.883 minus 1. Okay, so this is what you have here. Okay, so let us compute these values. Let us calculate this. First of all, let us calculate the term 1.552 power 1.4, okay, minus 1 divided by gamma 1.4 times of 0.552. So this is the value. Now divided with 12.04 whole power 0.4 divided with, so this value divided with 12.04 whole power 0.4. okay, so this is the total value. Now subtract this from 1, so subtract this value from 1. okay, so 0.5933, correct? 0.5933, which is 59.3% almost, correct? So please cross match the value. Is the first case efficiency is 0.59? So please type in the chat box. Did you all get this? Yes, so please type in the chat box. Is this clear to you? Are you all getting the same value here? Okay, so now let us calculate a second case efficiency. Okay, so let us store this value for some time. Then let us calculate this 1.883 whole power 1.4 minus 1 divided by 1.4 times of 0.883. okay, 0.883. so if you do this 1.15, now divide this with 12.04 whole power 0.4. okay, so this gives you 0.426. so subtract this from 1. so when you subtract this from 1, actually here 0.5738, 0.5738 actually. okay, so 57.38%. clearly you can understand this 0.59 is actually higher than this 0.57, so efficiency already came down. okay, now let us see what is the percentage in the drop. so 0.5933 minus 0.5738 divided by 0.5933 multiplied with 100. so this gives you, let us calculate this value. so this is the new value. so subtract this value from the stored value previously. okay, so divided with previous value, so into 100. so this gives you 3.286%, 3.287% actually here, correct? so 3.287. okay, so into 100 we have already done, correct? yeah, into 100 we have done. so 3.287% is the efficiency fall when you have increased the cutoff to 8%, correct? so please type in the chat box. Is this clear to all of you? Did you all get 3.28% fall in the efficiency of the cycle? Yes or no? okay, got it? I think someone told 6 point. I think there could be some calculation problem there. okay, now I'll ask you one question. Try to understand this. Let us suppose, if you look, this is the formula for the thermal efficiency, of course multiplied with gamma. Now one question I want to ask you. Let us suppose if cutoff ratio is tending to 1, okay, means if cutoff ratio is almost equal to 1, then what happens to this term? Please tell me. We'll go to the next question, it's okay, but try to understand something here. If you put cutoff ratio is almost equal to 1, cutoff ratio tends to 1, then what happens? What is the thermal efficiency in that case? Will this fraction exist when you put O equal to 1? For example, when you put O is equal to 1, will this fraction exist? When you put O equal to 1, will this fraction exist? No, correct? It won't exist. But what is the meaning of this cutoff ratio equal to 1? Look, try to understand here. When rho tends to 1, because I want to discuss one point here. When rho tends to 1, one thing is very clear, rho power gamma minus 1 by gamma times of O minus 1. This value tends to 0 by 0 form, correct? This gives you 0 by 0 form. Now whenever that fraction is giving 0 by 0 form, what you do generally in mathematics and all, you might have seen some limits. So if you are getting 0 by 0 form, then what you will do actually? If you are getting a 0 by 0 form, then what you will do? L'Hospital, correct? Very good. So you will apply L'Hospital rule here. So limit rho tends to 1, rho power gamma minus 1 by gamma times of rho minus 1, correct? Now if you differentiate, if you apply L'Hospital rule, try to understand carefully here. I'm going to tell you one very important result, so please see here. If you take L'Hospital rule, we get limit rho tends to 1. Differentiation of this term is gamma into rho power gamma minus 1 divided by gamma is constant into differentiation of rho is 1 minus derivative of 1 is constant. So this is 1 actually here. So if you see gamma and gamma gets cancelled, then if you put rho equal to 1, 1 power 0.4 which is 1. So whenever this rho is tending to 1, means whenever rho value is equal to 1, then definitely this bracket whichever is here is coming out to be 1. Okay, if this bracket is 1, then what is the formula here? 1 minus 1 by r power gamma minus 1. Have you seen this anywhere? Let us suppose if this bracketed term is 1, then have you seen this formula anywhere? 1 minus 1 by r power gamma minus 1. What is the meaning of, for which cycle is that the formula for thermal efficiency? Otto cycle, correct? Yes. So whenever cutoff ratio is tending to 1, that means the cycle converts from diesel to Otto cycle. How? Physically how it happens is, see, I will tell you. Look, whenever you are injecting fuel, there is a movement of the piston, correct? What is Otto cycle efficiency? Of course. Okay, so see here carefully. When rho is tending to 1, what is the physical meaning of that? Look, whenever rho is tending to 1, rho is V3 by V2. You know this, correct? Whenever this value is tending to 1, this means, can I say V3 is tending to V2, which means V3 and V2 are almost the same? Can I say this? Can I say V3 and V2 are almost the same whenever rho is tending to 1? Yes or no? Correct? Can I say this? Whenever rho tends to 1, then definitely what happens? This V3 and V2 are very close to each other. Now, tell me this question. Whenever V3 and V2 are very close to each other, means during your fuel injection, during your heat addition, your piston is not moving by sufficient amount. Yes or no? Means your piston has almost moved very less amount. Yes or no? Which means the heat addition what you are doing is happening at constant volume actually. Yes or no? Because if V2 and V3 are very close to each other, that means physically during your fuel injection, the piston is not moving. So that means you are actually injecting the fuel, or you are actually adding the heat when at very small volume change. So you can approximate that as heat addition at constant volume. That's how the main difference between the operation principle in diesel and Otto cycle, between diesel and Otto cycles, is the process of heat addition. So whenever rho is very much close to 1, then definitely the heat addition is at constant volume. That's how physically a diesel cycle gets converted to an Otto cycle actually. Okay, and formula wise you can see this formula gets converted to the efficiency of a Otto cycle. Clear to all of you? So is this clear to all of you? Did you all understand this? How when rho tends to 1, mathematically what's happening, and physically how the cycle gets converted? Okay, fine. So let's go for the next question. Okay, clear? Okay, so let's go for the next question. So let us solve this question. A utility runs Rankine cycle with a water boiler at 3 megapascals. Okay, so specific enthalpy of at the boiler is 33344 kilojoule per kg, and S is 7.08 33 kilojoule per kg, and the cycle has the highest and lowest temperatures of 450 degrees Celsius and 45 degrees Celsius respectively. At 45 degrees Celsius, HF, HFC, VF, P saturation, SF, SFG values are given. So properties of the steam are generally given at the 45 degrees Celsius. Okay, then the ratio of plant efficiency and the efficiency of a Carnot cycle with the same temperature limits is dash. Okay, so first of all, whenever the Carnot cycle is operating between same temperature limits, then you know heat addition and heat ejection happen at constant temperature in case of a Carnot cycle, correct? So let us see. First of all, let us try to plot this Rankine cycle. Okay, so it is running a Rankine cycle with a water boiler at 3 megapascals. Okay, and this cycle has the highest and lowest temperatures of this identity. Okay, then the ratio of plant efficiency. So first of all, let us try to plot a TS for the Rankine cycle. So if you plot a TS, let me draw this a bit bottom. So I have some things to plot. Fine. Okay. Now let us see. Let us put the dome. So TS. Look, one very important point I would like to tell you, especially in interviews like BRC, which I have cleared. So if you see, whenever you are drawing this dome, you should be very careful that if you have seen, I have drawn this dome in a particular way. Left part I have made almost straight and the right part I have made lot of inclination. Correct? This shape is very much important actually. Okay, normally any fluid, whenever it's going phase change from liquid to vapor, we will get some dome like this, which is called the vapor dome. Okay, and especially in refrigeration cycles, whenever refrigerants are analyzed using this TS diagram, this curve plays a very important role. There is something called superheat horn, and of course you have some loss in refrigeration effect. Okay, loss in refrigeration effect in refrigeration cycles. These loss and super horn, they depend exclusively on this shape of the curve. Okay, so anyhow, this shape is important. Normally what happens is, on the left hand side we have liquid phases. So these liquids, they do not show much change in any properties. So this is almost like a vertical line, but this we have a slant expanded line. Okay, now if you see the condenser limits and boiler limits, let us suppose the condenser is somewhere here, condenser and boiler, for example. Okay, so let us suppose you have a boiler here, boiler. Okay, so this is P boiler, pressure at which the boiler is operating, and this is the pressure at which condenser is operating. Okay, now you have a normal Rankine cycle. So let us see, you have got some Rankine cycle. So there is some pump which is taking the fluid from low pressure to high pressure. Okay, so if this is state 1 and this is state 2, for example, now along the constant pressure we are heating the system, we are supplying heat to the system. So we get somewhere here, for example. Okay, so we get somewhere here state 3. Then from here we have expanded isentropically in a turbine. So let us suppose we have expanded isentropically in a turbine. Okay, so 3, this is location 3, for example, and 3 to 1, 4. Okay, so let us keep this point 4. 3 we have already used there, so 4, and 4 to 1 we have some condensation. Okay, so condensation, before sending the fluid back to the pump we actually condensate. Okay, so this is how we have a normal standard Rankine cycle. Now before going for this question, solving some mathematics and all, let me talk about some good points here actually. Okay, so if you normally, the main purpose of running a Rankine cycle in a power plant is to continuously produce rotation for the turbine, correct, for the turbine shaft actually. Okay, so whenever the steam goes and hit the blades of the turbine, obviously turbine shaft rotates. Okay, now tell me one thing, you have a condenser here, correct, you have some condenser, outlet from the turbine enters the condenser, and again saturated liquid comes out of the condenser. Now try to tell me this, practically speaking, heat supplied to the boiler and the work output of the turbine actually matters to you. This heat ejection do not matter, yes or no, practically speaking, because if you see in a turbine, the amount of rotation for the turbine is due to this work done in this expansion process. Okay, so this heat ejection is not much significant for you. So I have one idea. Let us suppose, instead of running this plant by putting a condenser here, what I want to do is, let us suppose I have a fresh water source. Okay, very large water source. Okay, very fresh water and a large water source. Then can I leave the outlet of the turbine into that lake and again pick some new water from the pump? Okay, can I do this? Means basically, instead of having a turbine here, I will put a large amount of lake. Okay, fresh water lake, no impurities, nothing, so that I will put my exit of the turbine into that lake and I will take inlet for the pump from some other location. Can I do this? Can I do this? Means, is there any mandatory need of the condenser in the power plant? What happens if you take off the condenser actually? Because condenser is not, if you see, boiler is important and turbine is also important. Yes, your purpose is solved. Once the steam comes out of the turbine, you don't have any use out of it. Okay, then because it is getting ejected in the condenser, then can you run a power plant without having the condenser? If you cannot run, then what is the problem? So please tell me. Did you all understand my question? So please type in the chat box. Is this clear to all of you? Did you all get my question? Why is it mandatory to use a condenser in a power plant? Or if it is not mandatory, then please justify. What can you do? So please type in the chat box. Any idea? Okay, fine. Look, let me give you a hint, or let me answer this. First of all, if you see the operating conditions of a condenser, please tell me, this condenser operates below atmospheric pressure. Yes, very good. Okay, it operates much below the atmospheric pressure. Okay, so if it operates much below the atmospheric pressure, then what is the advantage for you? Pritham, good. But if the condenser is operating at a pressure lower than the atmospheric pressure, what is advantage for you actually? What is the advantage that you will get if condenser is operating below atmospheric pressure? We can operate without condenser, but work output will be less. Exactly. Okay, people, if you feel that condenser cost can be eliminated by taking out the condenser, but actually practically what happens is your efficiency of the cycle will fall down. Okay, drastically. Why? Because if you see, very good, as people some of you have told. So see here, normally we know this formula, thermal efficiency is equal to 1 minus heat rejection temperature by, since here in Rankine cycle there is one concept called mean temperature of heat addition. I don't know whether you might have gone through this or not. So what happens is, whenever the heat addition is not at constant temperature, we assume a particular temperature at which the complete heat is added with the same effect on the cycle. Okay, so this is called mean temperature of heat addition, which we will discuss in a detailed course, maybe in some crash course or somewhere in after some time. Okay, so if you see, this is written as TH of the mean as per your second law. Okay, now if you see, this mean temperature of heat addition remains same if your boiler doesn't change, but if you take out this condenser, practically this condensers operate around at 40 kilopascals, 30 kilopascals of this. That is normally it won't happen, but 35 to 40 kilopascals range. Okay, so whenever this heat rejection happens at this particular range, the saturation temperature corresponding to this pressure is lower than the saturation temperature at atmospheric pressure. When I am leaving the exit to the water, condensation is happening at atmospheric pressure. Okay, because it is open to atmosphere. But when you are putting a condenser, you are actually bringing the system to much lower pressure, so that this saturation temperature of phase change is less, so this TL is less. So if TL decreases, this template value decreases, so thermal efficiency of the plant increases. Okay, and of course, if you can also see, whenever this constant pressure line, instead of 40 kilopascals, if it is at 100 kilopascals, something like this, let us suppose if this is at 100 kilopascals, something like this, then your turbine do expansion only from this point to this point, then this amount of work which you are supplying is lost, but the boiler heat what you are supplying is same. Okay, so for the same heat supply, you are losing some part of work here. That's why practically you cannot take the condenser. Okay, by taking condenser, you may feel that condenser cost can be saved, but your efficiency of the cycle falls drastically. Clear? Okay, so did you understand? Because this is one very famous question in many of the interviews, that they'll ask you why condenser is mandatory in a power plant. Okay, this is the reason, and the answer is from the second law of thermodynamics point of view. Clear? Okay, so is this clear to all of you? Did you understand how turbine work output falls and the cycle efficiency falls as I said? Okay, now let us solve this question. These are some points I thought of discussing when I'm talking about Rankine cycle. Okay, so let us see. there is a temperature T. Okay, so now let us see. First of all, whenever Carnot cycle is operating between same temperature limits, T max is equal to, how much is this? T max is 450 degrees Celsius, 450 degrees Celsius, which is 723 Kelvin. Correct? Because if you see, 450 plus 273 gives you 3, 5 plus 7, 12, and 1 gives you 7 here. And T minimum is equal to how much? 45 degrees Celsius. Correct? So this is 45 degrees Celsius. So 45 degrees Celsius is equal to 273 plus 45. 813. So 318 Kelvin. Now, if Carnot cycle is operating between these two temperatures, what is Carnot efficiency? Efficiency of Carnot is equal to 1 minus T minimum by T maximum. Okay, so this is 1 minus 318 by 723. So if you do this calculation, correct? So let us do this calculation, all of you. So 318 by 723. So 318 by 723. Okay, so take a negative of this and add 1. So 56% almost. 0.5601. 0.5601 is the efficiency of the Carnot. Almost some 56% efficient. Okay, now let us talk about the Rankine efficiency. So what is the Rankine efficiency in this case? W net by heat supplied to the boiler. Okay, so heat supplied to the boiler, W net by QS. Now what is W net actually here in this case? W net is WT, what the turbine has produced, minus whatever the consumption that's there in the pump. Okay, so please tell me one thing. 0.6239. Okay, let us see. So first of all, tell me one thing. In a Rankine cycle, we generally neglect the pump work. Correct? The reason for neglecting the pump work is, actually we know, since pump is an open system, the work interaction of a control volume is minus integral VDP, which is known to you. Correct? And here the pressure ranges from condenser pressure to boiler pressure. But if you see, this specific volume will be very less because pumps handle liquids, and whenever the system is in liquid phase, the density of the system is very high, which means the specific volume, which is reciprocal of density, is very low. For example, if you take the fluid as water, density of water is 1000 kg per meter cube. But if you talk about the specific volume, 10 power minus 3, which is very low value when you substitute here. That's why the pump works in generally Rankine cycles is neglected, because pumps handle liquids and the specific volume of liquids will be very much small. Okay, so this is the reason. If you asked about the compressor in Breton cycle, can you neglect the compressor work in Breton cycle? Can you neglect the compressor work in Breton cycle? Type in the chat box. Can you neglect the compressor work in that Breton cycle? So type in the chat box. Can you neglect it? Can you neglect? Can you neglect compressor work input in case of Breton cycle? Yes, we cannot neglect. Okay, because compressors handle gases, and for gases densities are very low and specific volume is comparatively very high. Okay, here specific volume is 0.001 almost, but if you take substances like air and all, then it is around 0.98, 0.96 of that range. So you cannot neglect actually. Okay, so anyhow, let us see. Anyhow, here let us see here. So this is W net is turbine work H3 minus H4 divided by minus H2 minus H1. For example, if you write the formula completely, by heat supplied is H3 minus H2. Correct? So this is the enthalpies. This is work which is produced. This is the work interaction which is happened in this turbine, and this is the work interaction of the pump, and this is the heat addition in case of a boiler. Okay. Now here if you see, let us talk about the things. HF is given 188.42 and HFC is given 2394.77. VF, VG are also given. It runs on a Rankine cycle with a water boiler at 3 megapascals. So at that condition, at superheated condition, this is specific enthalpy and this is specific entropy. Okay, so let us see this pump work. If you neglect this pump work, since pressure values are not okay, pressure values are given, right? P saturation is also given at this condition. Okay, so P saturation is 9.6 kilopascals. Okay, let us not neglect, let us take this pump work also into consideration. H2 minus H1. So first of all, what is H2 minus H1? Okay, so let us calculate. H2 minus H1 is equal to, this is running on water, so V into P boiler minus P condenser. P boiler minus P condenser. So what is P boiler minus P condenser? Let us see here. Specific volume of water is 10 power minus 3 into boiler is operating at 3 megapascals, which is 3000 kilopascals, minus this P saturation at the condenser is how much? 9.6 kilopascals. See, such a low pressures, 9.6 kilopascals. So this answer, if you take in kilojoule per kg, then if you see 3000 minus 9.6, 3000 minus 9.6, so this divided by 1000. Okay, so 2.99 kilojoule per kg. Okay, then W of, or generally H3 minus H4. Now to calculate H4, we should know one very important parameter, which is called the dryness fraction. Correct? We should understand what is the dryness fraction at this location. Dryness fraction at this location. Okay, so how to calculate this dryness fraction? Then we can write, if you equate specific entropy at location 3 and location 4, you can get specific the dryness fraction. Correct? So S3 is same as S4. So what about S3 at the exit of the boiler? 7.0833. 7.0833 is equal to, at this saturation conditions, SF is 0.6386. 0.6386 plus dryness fraction at that location into SFZ. So what is SFZ value? 7.5261. 7.5261. Okay, so this implies your X dryness fraction is equal to, so let us perform some calculation. 7.0833 minus 0.6386. 0.6386. Okay, so this value divided with 7.5261. 7.5261. Okay, so 0.856. 0.856 actually here. Okay, so this is the dryness fraction here. Now if this is dryness fraction, this implies, what about your H4? HF at this condenser pressure plus X into HFZ. Correct? So what is HF at this condenser conditions? HF at this condenser conditions is 188.42. 188.42 plus X dryness fraction is 0.856 into HFZ. So what about HFZ? HFZ in this conditions is 2394.77. So 2394.77. Okay, so if you simplify this, then we get H4 value. Okay, so this value is in kilojoule per kg again. Kilojoule per kg. So let us do this. So dryness fraction multiplied with 2394.77. 2394.77. Okay, so 2050 plus 188.42 plus 188.42. Okay, so 2239. 2239.09. So 0.1 kilojoule per kg. So we know H4 value. H3 value they have given you. H2. So how to calculate this H2? HF plus this work input to the pump. Okay, so specific volume they have already given 0.001, almost 1000, because density of water is 1000, so reciprocal of that is this value. Okay, now if you put all these terms together, Carnot efficiency. So what about Carnot efficiency? Let us see. Carnot efficiency, Rankine efficiency is what we want. Rankine efficiency is equal to H3 minus H4. So what about H3? This value 3344 minus H4. What about H4? 2239.1 minus pump work. What about pump work? 2.99. Okay, you can write 3, almost 0.01, doesn't give you much difference, divided with heat added in the boiler. Okay, so what about heat added in the boiler? This H3 minus H2, correct? So H3 minus H2. So what about H2? H2 is H1 plus 3 actually. Okay, so what about H1? HF at this location, HF at this location is 188.42 plus 3, 192.42. Okay, so 191.42, we can write 191.42. so this gives you the thermal efficiency of this cycle, okay, of the Carnot cycle, of this Rankine cycle. Okay, so therefore thermal efficiency of Rankine cycle is equal to, let us calculate this value. So let us calculate 3344 minus 2239.1 minus, okay, so minus 3, so this value divided with 3344 minus 191.42, okay, so 191.42, so 0.3495, 0.3495, so 35% almost. Okay, so this is 0.3495, so the Carnot efficiency is around 0.56% we got, and Rankine efficiency is 0.3495 actually. Okay, so therefore efficiency of Rankine to efficiency of Carnot, correct? This is what they are asking in the question. So they are asking you the ratio of plant efficiency and efficiency of the Carnot cycle. Okay, so plant efficiency is this, whatever we have calculated, so 0.3495 divided with, we got some value here, okay, for the Carnot cycle 0.5610, 0.5610, correct, 0.5601. so this value, if you divide this divided with 0.5601, okay, so 0.5601, so 0.624, 0.624 is the ratio in this case. Clear? So 0.624. One thing you can see, definitely the Rankine efficiency will be less than Carnot efficiency. The reason is, you might have studied the concept of availability and irreversibility. Okay, so in case of availability, yes, 0.624 around is correct. Yes, Sukumar correct, 0.624 is correct. Okay, the reason why efficiency of Rankine, look, it's very good check in exam. Let us suppose, for example, if you get this value higher than Carnot, definitely there is some mistake in the calculation. Okay, so you have to check your calculation, because practically what should happen, you know the concept of availability, correct? Higher the temperature of your heat addition, then definitely higher will be the cycle efficiency. Okay, so because the capability of high temperature energy to do work will be more. Okay, so in Carnot assumption, we assume complete heat is transferred at constant temperature, at uniform temperature. Okay, but in case of Rankine cycle, at one particular point you are touching 450, that's it. Remaining maximum amount of heat is added at low temperature. Okay, so that's why heat addition at low temperature is not much effective as compared to the heat addition at higher temperature. This is based on the concept of availability, so that's why definitely Carnot has maximum. If look, Carnot, they am told all reversible cycles have equal efficiency, okay, operating between same temperature limits, but here the heat addition is actually changing. Okay, here you are not adding the heat completely at 450 degrees Celsius, you are acting only very little part at 450 degrees Celsius, all remaining part you are adding at low temperature. Okay, so that's why Carnot efficiency will be definitely more than this Rankine efficiency. Clear? Your concept of availability actually answers this. Okay, and one just practical thing I want to tell you before going for the next question. We'll move for the next question, but just one thing, this guy, Dyna's fraction at the exit of the turbine is very important. Okay, this X value is normally maintained 85 to 90%, or sometimes in case of reheating and all 93% to that values, but practically this X has very important, X is very important actually. Okay, because when you change, let us suppose if Dyna's fraction is low, that means this turbine, instead of hitting this point here, this turbine point hits somewhere here. Okay, whenever the point shifts from this location to this location, the Dyna's fraction of the steam actually decreases. Okay, so what is the meaning of this decrease in the Dyna's fraction? Whenever Dyna's fraction decreases, the liquid molecules, means the liquid phase molecules in the steam increases. Okay, and as the substance is getting converted to liquid phase, the density of the system increases actually, because obviously specific volume will decrease, so density will increase. So the liquid particles has high density, so whenever you are throwing high density particles on the blades of the turbine, then the blades of the turbine can get eroded. Okay, so this is one very important problem that you face in industries. Blade erosion is one very common problem. You generally do maintenance all the time. When I was in HPCL, we were maintaining some pumps Pumps get, sometimes you don't even imagine the view of the pump after getting, eroded. Okay, it's almost like half of the material is blown off from the pump. Okay, so basically liquid particle hitting is very, very dangerous in any equipment. So that's why this maintaining the Dynamis fraction in the expansion during the expansion process in Rankine cycle is very, very important. Clear to all of you? So are you all clear with this question? So please type in the chat box. Is this clear to all of you? Clear? Okay, so let's go for the next question quickly. So let us see this. To approximate an actual spark ignition engine, consider an air standard Otto cycle that has a heat addition of 1800 kJ per kg of air, a compression ratio of 7, and a pressure and temperature at the beginning of the compression process of 90 kilopascals and 10 degrees Celsius. Then the mean effective pressure is dash. So mean effective pressure, one very important concept again, for which is actually responsible for the capacity of converting heat to work actually. Okay, so this mean effective pressure. So first of all, let us work it out. Mean effective pressure is net work divided by the swept volume, correct? So net work divided by the swept volume. So let us plot this Otto cycle first of all. So T S or PV, let us plot PV first, P and V. Okay, now you fix the minimum and maximum distances of the piston. Let us suppose if piston is oscillating between these points, then state 1, state 2, then you have some constant volume heat addition. It's an Otto cycle. So then after we get a constant, isentropic expansion, and then again some constant volume heat rejection. Okay, so we have a constant volume heat rejection. Clear? So we get a constant volume heat rejection. Now let us see, they have given you certain quantities at the beginning of the compression. Let us write the points. This is isentropic compression, constant volume heat addition, constant again isentropic expansion, and constant volume heat rejection. Okay, so this is constant volume heat rejection. Okay, now we know that at the beginning of the compression, P and T are these values. So P1 is equal to 90 kilopascals, and what about T1? T1 is 283 Kelvin. 283 Kelvin. Okay, so this is 283 Kelvin. Then the mean effective pressure. Okay, so to calculate mean effective pressure, we should know what is the net work interaction that's happening in this cycle and the Vs. Okay, so here if you see, net work interaction is equal to net heat interaction of this cycle anyhow. So sigma W actually. Okay, so compression work and out W out. Okay, so we know sigma W is equal to work out minus work in, which is, of course, if you do for specific terms, then CV times of, okay, CV times of outlet is from 3 to 4, so T3 minus T4 minus CV times of this inlet, since you have taken minus n already, T2 minus T1 divided by, okay, so this is the work. Okay, and Vs is how much? If you take specific here, then here also it can be taken specific. So V2 or V swept volume is V1 minus V2, correct? Now V1 minus V2. So let us see, the substance is air. So characteristic gas constant is 0.287 kilojoule per kg Kelvin. And what about gamma? Gamma is 1.4 actually. Okay, so gamma value is 1.4. Now let us try to solve this. V1 minus V2 is this. So first of all, how to get V1? We get P1 and P2. So V1 can be taken from this equation. V1 is equal to RT, or PV is equal to RT. So RT1 by P1. Okay, so which is 0.287 into 283 by P1, which is 90 kilopascals. So this is in some meter cube per kg. Okay, now let us calculate this value. 0.287 into 283 by 90. Okay, So 0.902. 0.902. Correct? 0.287 into 283 divided by 90. So what about V2? They have talked about compression ratio. Correct? Given compression ratio of 7. So R is equal to 7. This implies V1 by V2 is equal to 7. So V2 is V1 by 7. So if you divide this value with 7, then divided by 7 gives you 0.18129. 0.129 meter cube per kg. So T1 is known to you. You don't know what is T2. How to get T2 value? So let us see. For process 1 to 2. For process 1 to 2 actually here. Or better, let us do one more thing. They have given heat addition, correct? Heat addition of 1800 kilojoule per kg. So we know thermal efficiency. Thermal efficiency of auto is 1 minus 1 by R power gamma minus 1, which is W net by QS, heat supplied. Correct? Can we talk this relation? Yes or no? So please type in the chat box. Can I use this relation? W net by QS. Can I use this? Because thermal efficiency formula is basically for the amount of heat input, what is the maximum net work output you are taking out of the engine. Correct? So can I use this expression? Yes or no? So type in the chat box. Can I use this? Because we have the compression ratio and it's an A standard cycle, so we know gamma. Okay. So when you use this, this implies your W net is equal to QS. If you had specific terms, then QS times of 1 minus 1 by R power gamma minus 1. Okay. So if you substitute QS, it is given the heat addition of 1800 kilojoule per kg. Okay. So 1800 into 1 minus 1 by compression ratio 7 power gamma minus 1, 1.4 minus 1. So this gives you W net. This is in kilojoule per kg. Okay, because this is also in kilojoule per kg. So if you perform this calculation, let us perform 7 power 1.4 minus 1, 0.4. Then reciprocate this, subtract this from 1. So subtract this from 1 actually here. Okay, so subtract this from 1. Okay, and multiplied with 1800. So 973.52. 973.52 kilojoule per kg. So this is the net work interaction in that case. 973.52 kilojoule per kg. Okay, so whenever this is 973.52 kilojoule per kg, then V1 and V2 values are known. This V1 minus V2 can be calculated, V1 and V2. Therefore, mean effective pressure in this calculation is W net by V1 minus V2. Since this is in kilojoules per kg, answer could be in kilopascals. So 973.52 divided with 0.902 minus 0.129. Okay, so this answer is in kilopascals. Whatever you get, that will be in kilopascals, because this is substituted in kilojoule per kg. Clear? So let us perform this calculation. 973.52 divided with 0.902 minus 0.129. 0.129. Okay, so this gives you 1259.4. 1259.4 kilopascals actually here. Correct? 1259.4 kilopascals. Clear? So let us see. We have got some options here. So 1259. So 1258. Okay, they might have taken some decimals here, maybe some 2 decimal places or something. So we got some little difference, but that could be very much compensated. So 1259.4 kilopascals is what you have at the mean effective pressure acting on the piston. Clear? So physically, what is mean effective pressure? Normally during the expansion stroke, means during the work production stroke, the pressure on the piston actually varies. Correct? So we assume there is some uniform pressure which is acting on the piston throughout the expansion stroke, okay, for producing the same work output. That's what we call mean effective pressure. So around 1260 kilopascals could be the range of mean effective pressure. Okay, fine. So is that clear to all of you? 1259 kilopascals almost. Okay, so that could be correct answer. Next, let us go for the next question. A steam power plant operates on an ideal reheat Rankine cycle between the pressure limits of 15 megapascals and 10 kilopascals. Steam enters in high pressure turbine with specific enthalpy of 3310.8 kilojoule per kg and then enters the reheater with specific enthalpy of 2817.2 kilojoule per kg. This reheated steam is now entered in low pressure turbine with specific enthalpy of 3466.61 kilojoule per kg. The properties of the condensed water, so at the condensation stage, is HF, VF and HFG values are given. So what they are asking you finally, if mass flow rate of the steam through the cycle is 12 kgs per second, the total rate of heat input in the boiler will be dash in kilowatts. Okay, so kilojoule per second. So they are asking you what is the total amount of heat input to the system. Okay, so let us solve this. If you are doing a reheat Rankine cycle, let us see, plot TS. Okay, so let us suppose if this is your TS, so you have a condenser. So if you see, you have a condenser here. Then you have a boiler operating pressure. And there is some intermediate pressure at which you have, there is some intermediate pressure after which you have started reheating. Okay, generally in case of ideal reheating, you expand it up to this position and then you do the reheating again. Okay, so fine. So this is intermediate pressure, P intermediate. This is boiler pressure and this is condenser pressure. Okay, so boiler, intermediate and condenser pressures. Okay, now if you see, this is operated between 15 megapascals and 10 kilopascals. So this is 15 megapascals and this is 10 kilopascals. Okay, now, so enthalpy values are given. They are asking you the total heat input to the boiler. Okay, so total heat input to the boilers. Okay, so let us see, if you draw a cycle here, let us suppose there is one pump which is taking the system from state 1 to state 2, state 1 to state 2. Then after, there is some heating in the boiler. There is some heating that's taking place in the boiler. So from here, let us suppose they have expanded in a high pressure turbine. Okay, so this is some high pressure turbine, for example, let us say up to this point. This is some high pressure turbine. Okay, to this point. Then after, so this temperature is how much they have heated. Okay, to some temperature they have heated. The steam now re-enters. Okay, so temperatures they haven't mentioned, correct? Steam enters in high pressure turbine and then enters the reheater. This reheated steam now enters the turbine. Okay, so temperatures they haven't mentioned. They talked about only enthalpies. Okay, so they have again heated this to some particular enthalpy and then expanded in a turbine. Okay, so they have expanded that in a turbine. As I told you, in case of reheating, dryness fraction generally increases. Okay, and finally it got condensed. It got condensed. Fine. So what they're asking you, they're asking you what is the total amount of heat supply. Okay, so let us see. This is state 3, initial first stage of expansion in high pressure turbine. Then in low pressure turbine, again you have expanded this. And this is state 6. Okay, now what is the total heat that you have supplied? QS is equal to mass flow rate of the substance into. So first of all, you are heating in the boiler H3 minus H2, H3 minus H2. Then again you are heating in the reheater, so H5 minus H4, H4. Okay, so these are the values, H3 minus H4. Now let us see H3 minus H5 minus H4, right? H5 minus H4. Okay, good. So m dot, what is the mass flow rate to the boiler? 12 kgs per second. So 12 kgs into H3. So what is H3? inlet to the high pressure turbine, correct? So how do you decide which is high pressure turbine and which is low pressure turbine? Depending upon the steam entry. Okay, steam is entering here at this 15 megapascals pressure, but steam is entering to this turbine at some intermediate pressure which is less than 15 megapascals. Okay, so that's how normally, if you see, depending on the inlet condition of the steam, we decide which is high pressure turbine and which is low pressure turbine. Okay, so now if you see this H3 is inlet to the high pressure turbine. Okay, so let us see. Steam enters in high pressure turbine with a specific enthalpy of 3310.8. Okay, so H3 3310.8 kilojoule per kg. Okay, this is kilojoule per kg. Next, we need one more quantity which is H2. So what about H2? A pump. Okay, so pump condition. So how do we identify the pump actually? Look, we can do this by writing H1 plus specific volume Vf into the pressure difference. Okay, so H2 can be written as H1 plus specific volume at liquid phase into boiler pressure minus condenser pressure. So what about H1? H1 is nothing but HF at this condition, 191.81. 191.81 plus Vf. What about Vf? 0.00101. 0.00101 into 15 megapascals, which is 15,000 kilopascals minus condenser pressure. Okay, so the condenser is operated at 10 kilopascals. Okay, so this is 10 kilopascals. So if you perform this calculation, we get the answer in kilojoule per kg. Okay, so let us perform this calculation quickly. So please do along with me. So 15,000 minus 10, 14,990. 14,990 times of 0.00101. Okay, so 15.14 kilojoules. Okay, so into this quantity plus 191.81 plus 191.81. Okay, so 206.95. 206.95 kilojoule per kg. Okay, so this is the specific enthalpy at location 2. H5. So what about H5? H5 is inlet to the low pressure turbine. So let us check this question. This reheated steam is now enters in a low pressure turbine with specific enthalpy of 3466. Okay, so H5 value is 3466 point. So what about this? 3466.61 kilojoule per kg. 61 kilojoule per kg. Okay, and what about H4? H4 is just a minute. H4 here is the entry to the reheater. Okay, so let us see. And then it enters to the reheater with specific enthalpy of 2817.2. Okay, so this is 2817.2. 2817.2 kilojoule per kg. So we got all the values. Okay, so three values are directly given to you. Look, when you try to visualize what's happening in the Rankine cycle, you can easily identify the locations at what state they are talking about. Okay, so if you substitute H3, H2, H5 and H4 values, H3 3310.8 minus H2, which is 206.95, plus H5 3466.61 minus 2817.2. Okay, so if you perform these values, answer is going to be in kilowatts because this is in kgs per second and these guys are in kilojoule per kg. Okay, so let us perform this calculation. So 3310.8 minus 206.95 plus 3466.61 minus 2817.2. Okay, so this is the value. So multiplied with 12. So if you multiply this value with 12, you get 45039. 45039.1 kilowatts. Okay, so this is the amount of heat what you have supplied. Almost some 45 megawatts of heat is what you are supplying into the boiler. Clear? Normally that's the case. Normally in case of power plants, the amount of heats will be in megawatts. Okay, so that's why when you see carefully, the operating conditions of the or the temperature of the boiler, it is maintained at some when the pressure of the boiler is maintained at some constant value. If the pressure actually falls slightly, then it will be very difficult. Okay, because obviously the availability of the things change actually. Okay, so that's what we have. So let us check the options. I think there are a few options to this. 45039. Yes, we got the exact value. 45039.1 kilowatts. Okay, so this is the correct answer in this case. Clear? Are you all understanding the questions, how we are doing them? Okay, so please type in the chat box. Fine. Is that clear to all of you? Are you all clear with the kind of questions we are solving? So please type in the chat box. If that's clear, then we'll go for the next question. Okay, so next question. So let us see. A classroom for 60 students is to be air conditioned to 22 degrees Celsius diurnal temperature and 55% relative humidity. Omega at that case is 0.009 kg per kg of dry air and specific enthalpy is 45 kilojoule per kg of dry air. So this requirement of air is there. This is done first by chemical dehumidification and then cooling it by passing over a cooling coil. Okay, so first of all they have dehumidified, means they have taken out some moisture out of the air and then they have passed it over a cooling coil. Okay, the outdoor conditions are 32 degrees Celsius diurnal temperature with specific enthalpy and omega specific volume and 22 degrees Celsius dew point temperature. Okay, so dew point temperature is 22 degrees Celsius. The quantity of fresh air required is 0.5 meter cube per minute per student and the class consists of 60 students. Take diurnal temperature of air after dehumidification as 50.8 degrees Celsius and bypass factor is 0.3. So good question. So let us see. Okay, so these are things which are of interest. What are the things of interest? Capacity of dehumidifier, okay, capacity of cooling coil, apparatus dew point temperature, capacity of the cooling coil. Okay, this is one contradicting option. Okay, fine. So let us see. First of all, guys, look here. There is a dehumidifier. Okay, there is a dehumidifier and there is a cooling coil also. There is some cooling coil. Now finally this is sent to the classroom. Air is taken from the atmosphere, then it is dehumidified, then after it is sent to the cooling coil and then it is sent to the classroom. Okay, so this is cooling coil and then it is sent to the class. Here it is atmosphere. Okay, so it is taken from atmosphere. It is taken from atmosphere. So what are the conditions at the atmosphere? Let us see. It is 22 degrees Celsius diurnal temperature and 55% relative humidity. So 22 degrees Celsius. Okay, this is required, correct? Requirement is 22 degrees Celsius and 55% relative humidity. So here the conditions that you need is 22 degrees Celsius and 55% relative humidity. Okay. Okay, so this is the required air at the classroom for the students end. Okay, now if you see, first by chemical dehumidification and then by cooling it over a cooling coil, the outdoor conditions are 32 degrees Celsius and omega is some value. Okay, so 32 degrees Celsius. So this is 32 degrees Celsius. This is a dehumidifier. Dehumidifier. So what is the meaning of dehumidification? You are actually taking out some water vapor from the air. Okay, so you are actually dehumidifying it, means you are taking out the water vapor from the air. Okay, so this is a dehumidifier and here we have a cooling coil. Cooling coil. Okay, so we have a cooling coil. So let us say this is T1 for example. Now let us see. Temperature after dehumidification is also given. Okay, take diurnal temperature of air after dehumidifier is 50.8 degrees Celsius. Okay, so this T2 after dehumidification, this is 50.8 degrees Celsius. Fine, great. 50.8 degrees Celsius. Then by passing it over a cooling coil, the quantity of fresh air required is 0.5 meter cube per minute per student. Okay, so what is the requirement of the fresh air? M dot air is equal to 0.5 meter cube per minute per student. Okay, so we need per student. Okay, so this is what we need. Now take diurnal temperature of air after dehumidification is 50.8 and bypass factor 0.3. Good. What are the options? Capacity of the dehumidifier in kg per hour. Okay, so what could be the capacity of this dehumidifier? Means the meaning is what amount of water can be taken out from the air by this dehumidifier. Okay, so that's what obviously capacity of dehumidifier. What is the purpose of dehumidifier? To take out the vapor from the mixed air. Okay, from the normal wet air. So they are asking what is the capacity of the dehumidifier. Okay, so capacity of the dehumidifier is nothing but, first of all we have a 60 students, so 0.5 into 60 meter cube per minute. Okay, so this much amount of air is required which is 30 meter cube per minute of air is required to you. Okay, so per minute. Okay, because this capacity is 60 students and this is per student. Okay, so this amount of air is actually required to you. Okay, now capacity of dehumidifier. Capacity of dehumidifier is how much? The purpose of dehumidifier is to take out the vapor. Okay, so this is nothing but m dot a times of omega 1 minus omega 2. Correct? Because here if the substance has a water vapor of omega 1 kg of vapor for kg of dye, here it is omega 2. So omega 1 minus omega 2 gives you the difference in the water vapor that is taken out from the air. Correct? Yes or no? So please type in the chat box. Is this clear? Omega 1 minus omega 2 gives you the difference of the water vapor which is taken out. Yes or no? So please type in the chat box. Okay, now if you see, this is equal to, okay, so m dot is 30 into omega 1. Initially what is omega 1 at the atmospheric conditions? At the atmosphere, the outdoor conditions, omega 1 is 0.0168. Okay, so this is 0.0168. Now what is omega 2 after dehumidifying? After dehumidification, what's happening here? First, by passing it, okay, so on 20 degrees Celsius, the quantity of fresh air is this much. Okay, what about omega 2? So this is a cooling curve. So here it is only cooling. Okay, so omega at this location and omega at this location should be same, correct? Because it is just a cooling coil, it is doing sensible cooling, it's not doing any humidification or dehumidification. So if this is omega 2 and this is omega 3, omega 2 should be same as omega 3 because this is just a cooling coil and there is some sensible cooling that's happening here. Okay, so there is no addition or deletion of any water vapor from the air. Okay, so that's why omega 2 can be replaced with omega 3, which is the required condition in the class 0.009. 0.009 actually here. Okay, so 0.009. So this value is going to be in meter cube per hour. Okay, because this is in meter cube per minute. Okay, so but we want kg per hour. Okay, so kg per hour. Let us do one thing. 30 by specific volume might be given here at the outdoor conditions. What is the specific volume? 0.89. Okay, so 0.89 into 60. Correct? So this gives you kg per hour. Okay, so this gives you kg per hour because this is in meter cube per minute. So meter cube per minute divided by specific volume gives you kg per minute. So if you multiply with 60, then kg per hour actually. Okay, 60 minutes. So kg per hour actually, right? So 30 divided by 0.89 into 60. Correct? So please type in the chat box. This is 30 divided by 0.89 is the specific volume. This gives you in kg per minute. So if you want kg per hour, then you multiply a 60 because 1 hour is 60 minutes. Okay, so this gives you 30 into 1800 divided by 0.89. 1800 divided by 0.89. Okay, so 2022.47. 2022.47 kg per hour. Okay, so if you put this value here instead of 30, if you keep in kg per hour, so 2022.47. So this capacity of the dehumidifier will be in kg per hour actually. Okay, so let us perform this calculation. This value multiplied with 0.0168 minus 0.009. 0.009 actually here. Okay, so 0.009. So 15.77. 15.77 kg per hour actually. Okay, so 15.77. So it's given 13.13. Correct? So please type in the chat box. 15.77 is the correct answer. Yes or no? Are you all getting 15.77? Because we have done 30 divided by this 0.89, which is the specific volume, gives you kg per minute actually. Okay, so if you want kg per minute, then if you multiply with 60, you'll get kg per hour. So did you all get this value? 15.77 kg per hour of air is actually supplied to the system. Yes, 15.775. Correct? Yes, 15.775. Correct. Okay, so 15.775 amount of kgs per hour is actually supplied to the ventilation system. Okay, now if you see, this is dehumidifier. Then what is the second case they are asking? Capacity of the cooling coil in tons of refrigeration. You know, 1 ton is equal to around 211 kilojoule per minute. So this, if you convert to second, 211 by 60 kilojoule per second or kilowatts. Okay, So 211 by 60. Let us see. If you do 211 by 60, 3.47, it comes out 3.51. So 3.516. 3.51. Okay, 1 ton is equal to 3.51 kilowatts. Okay, now they're asking you capacity of the cooling coil. So what is capacity of the cooling coil? The cooling coil have taken some heat from the system. Okay, so capacity of cooling coil is equal to capacity of cooling coil is equal to, so what could be the capacity of the cooling coil? Whatever heat is taken by the cooling coil, that is nothing but the capacity, correct? So m dot A into H2 minus H3, correct? This is what you have. So m dot A, mass flow rate of air, is 2022.47 into H2 or H3. Okay, so first of all, what is H3? H3 is this, which is required, 45 kilojoule per kg of dry air. Okay, so 45 kilojoule per kg of dry air. Now what about H2? H2 is just before entry to the cooling or after dehumidification. The outdoor conditions are this, and take DBT is this. Okay, so outdoor conditions are 75. Okay, so this is 75 kilojoule per kg Kelvin. So this is a dehumidifier, so they can write this as 75 actually here. So this value is how much? 75 minus 45 into 2022.47. Okay, so if you do this, this is in kilo, this answer is in kg per hour, I think, right? No, this is in kg per hour, but we want in kilowatts. Okay, so if you want in kilowatts, divided with 3600, we get the mass flow rate. Okay, so this value divided with 3600. Okay, so we'll get this answer in kilowatts, but if you want in refrigeration capacity tons, then 3.51 gives you in tons. Okay, so this is tons of refrigeration. Okay, so this is in tons of refrigeration. Okay, so if you do this in tons of refrigeration, then let us see. Okay, so 2022.47 divided by 3600. Okay, so this value multiplied with 30 divided with 3.51. Okay, so 3.51, so 4.80. What is the value? 4.802 tons of refrigeration is done. Means 4.802 tons is the capacity of this cooling coil that is placed here. Okay, so 4.8 tons. So let us check. 4.82. Okay, so 4.6, maybe one decimal place of here can change this first decimal. So 4.6 we can take reasonably the correct answer. Okay, 4.802, yes, of course. Okay, so if you slightly round off this 4.82, because there could be possible changes in the decimal values when you are taking this specific humidity calculations or anywhere here. Okay, so 2022.47, all these things. Similarly, some people put 3.6 here, 3.47, all these general adjustable values. So 4.802 is can be taken as correct answer here. Okay, so D is correct. 3.26 is actually wrong answer in this case. Then apparatus dew point temperature of cooling coil. Okay, so what is the apparatus dew point temperature? They have given you this bypass factor, correct? So once they give you the bypass factor, we can easily calculate what is the dew point temperature of this apparatus that's being used here. Okay, so bypass factor is given. So let us take one slide, empty slide. Bypass factor is given, which is 0.3, correct? So whenever this is the cooling coil, if you want to calculate the bypass factor, first of all, here the temperature is 50.8, here it got cooled to 22 degrees Celsius. Now out of this, some part of the temperature is used for cooling the system actually to bring this to the dew point temperature. So we can write this capacity, this bypass factor is equal to T3 minus apparatus dew point temperature by T2 minus apparatus dew point temperature again. Okay, so if you say this 0.3 is equal to T3, the system when it is supplied to the students, that's at 22 degrees Celsius. So 22 degrees Celsius minus, or 22 minus dew point temperature by T2 after dehumidification. What is the temperature? 50.8. So 50.8 minus dew point temperature. Okay, so this is from the definition of the sensibility of this by bypass factor of the cooling coil. Okay, so if you do this calculation, 0.3 times of 50.8 minus apparatus dew point temperature is equal to 22 minus temperature of apparatus dew point temperature. So this is 0.3 minus 0.3 and this is minus T. So if this comes to the left hand side, so 0.7 TADP is equal to 22 minus 0.3 times of 50.8. Okay, correct. So 0.3 times of 50.8 and this is 22. So 22 minus and TADP positive. Okay, so TADP apparatus dew point temperature is equal to how much? If you perform this calculation, let us see. 0.3 into 50.8, 0.3 into 50.8, so 15 point something 15.24. So subtract this from 22. So subtract this from 22, 6.76 divided by 0.7. So divided with 0.7. So 9.657, 9.657 degrees Celsius. So this is the apparatus dew point temperature at this conditions. Okay, so 9.657 degrees Celsius. So 9.657. So that can be written as 9.67. So C and D are the correct answers in this case. Clear? Yes or no? So please type in the chat box. Hi others. So is this clear to all of you? This calculation is slightly different because that decimals can change the first decimal when you're dealing with 0.00 such values, but these are the correct C and D are the correct options in this case. Okay. So dehumidification means basically, if you see, I would like to show it on a psychometric chart. You can see generally. If I want to explain, I'll take a minute and I'll explain. So this is the diurnal temperature and specific humidity omega. Okay. So this is specific humidity omega. Diurnal temperature in degrees Celsius and we got a omega here. Okay, specific humidity, and if you see, okay, so initially they are at some condition, then they dehumidified it, okay, at constant enthalpy generally, and then they have done some sensible cooling like this. This is what they have done actually. Okay, so state 1, for example, state 2, state 3, this is dehumidification process and this is sensible cooling process. Okay, so peak energy is sufficient for GATE 2023 exam preparation for thermodynamics heat transfer. For mechanical it's sufficient, but for XA I think you have to go for either Moyen and Sapir, or you can also go for Single sometimes. Okay, that could also be good. Single is fine. Moyen and Sapir is also fine. Okay, you can follow any one of these books for writing XE. Any more doubts? I think I can make my formula list from this lecture because it has covered all types of numericals. Yeah, definitely you can make a list. But of course, since this is a very short, short lecture for solving some 10 to 15 questions somewhere in between. Okay, so you won't get 100% out of it because I know I have to tell the fact because it's a very short lecture. But when you can follow the crash course that's being conducted few days ago on the main GATE Wallah mechanical channel. So from there you can get all your formulas and all. Okay. So I'm in BTech Mechanical Engineering branch in 4th semester and I am referring and practicing fluid mechanics and hydraulic machines from R.K. Rajput and R.K. Bansal, and I can't understand from foreign writer's book. Okay. Is this book sufficient for GATE exam, fluid mechanics and hydraulic machinery? To be honest, problems wise it is okay, but concepts wise it's not okay. Okay. So my sincere suggestion for you is at least follow one book out of the 3 books what I tell you. Frank and White, Modi and Seth, or not, sorry, Frank and White, S.K. Som, or you can follow Fox and McDonald. Okay, out of these 3 books, at least try to follow one book, or Single. Single could be much easy book. Okay, you can follow Single for some time. So then it could be very easy. Okay, because the main point I like in Single is what are the values they give in questions. Those are practical values. It's not like they tell you like, for example, the thermal conductivity of this material is something. They don't just give the value by default. Okay, they many times the values match with the actual physical values, because I identified this when I was doing my research. Okay, when you do fluid, when I was doing my experiments in fluid mechanics and all, many times I found this skin friction coefficient, drag coefficient values, all this they give exactly the values what you get in the lab. Okay, so this is one very good thing that happens. So I done GATE revision and PYQ. Now what should I do? Any suggestions? Try to attempt some test series. If you are doing already, that's good, then that could be fine. But try to write a test series. Okay, so that if you, the main purpose of writing test series is if you have any what do you say, if you are committing any mistakes, generally you will come to know in test series. Okay, because people feel that okay, I'm thorough with this formula, I'm thorough with this concept, but at the end they make some calculation mistakes and all that. Should not happen generally. Okay, fine. I hope all of you are liking this session, correct? Are you all liking the kind of questions that we are solving? Okay, fine. We have seen some good questions on cycles, Rankine, okay, psychometry, basically it's air conditioning, all these things. Okay, similarly we'll look at some Barton cycle questions also ahead. Okay, so clear. So shall we go for the next question? Fine. So let's go for the next question quickly. So let us solve this. At A at 300 Kelvin and 1 bar is compressed to a pressure ratio of 5, and after heating in the combustion chamber its temperature is raised to 1000 Kelvin. A then expands to 1 bar. Efficiency of the Barton cycle is eta 1. If efficiency of compressor means isentropic efficiencies of compressor and turbine are 85, generally these are of 85 to 90% somewhere, then the efficiency of the Barton cycle is eta 2. Then the magnitude of percentage decreased in efficiency is dash percent. Okay, so they are asking you, in first case it's an ideal cycle, straight away heating and falling, but in second case the compressor and the turbine, they got certain isentropic efficiencies. Okay, so whenever they got some isentropic efficiencies, obviously your heat input increases and work output falls. Okay, so obviously there is some decrease in the cycle's efficiency. They are asking you magnitude of percentage decrease in efficiency. Okay, means basically they are asking you eta 2 minus eta 1 by eta 1 into 100. This is what they are asking. Okay, so percentage decrease, but they are asking only magnitude. Okay, obviously this is negative value because 2 will be less than the case 1. Okay, so we'll see anyhow. So before GATE 2023, make a marathon session on fluid mechanics and hydraulic machines and thermal portion, only formulas and concepts. Yes, it is on the plan, but I don't take that. Okay, because I was engaged with some other classes as well. So there are other people who are taking it from the same my team. Okay, from the same team though. Now good. There you'll have some Mahavision sessions, so that you will definitely go for all the concepts and all the what do you say, all the formulas. It's like a quick go in a single video. You'll have a lot of questions actually. Clear? Fine. Also using calculator simultaneously is very effective. Yeah, obviously calculator. Look, I'll tell you one thing which I tell many times. When I got all India rank 40, I have committed 8.66 marks calculation mistakes. Okay, from that day I decided when I teach online session, because in offline obviously I cannot display calculator. From there I decided whenever I teach an online class, I'll definitely use an online calculator. Okay, so that's why I'm using online calculator. So along with me, you'll also be habitual to use that online calculator, because I'm telling you the only difference between all India first rank and all India 70, 80 within this range is only this calculator. Okay, knowledge levels they don't differ, but only the calculations they differ a bit. Okay, so anyhow, let us solve this question quickly. So initially have A at some condition, and this is brought to a pressure ratio of 5. Okay, so let us plot a TS for the Barton cycle. So let us plot some TS curve. Okay, so TS. Now what happens generally, Barton cycle operates between certain pressure limits, correct? So let us suppose you have some pressure curves like this. Okay, so there are some pressure. So initially let us suppose for the isentropic compression the state started here. So 1 and 2 here. Okay, now along this constant pressure we have a heat addition to state 3, for example. This is a constant pressure heat addition, of course, we know. Now we are expanding this turbine in a turbine. Okay, so for state 4 and state 4 actually here. Okay, sorry, this is expansion and this is again constant pressure expansion, and this is again isentropic. Okay, isentropic. Now practically what happens, because of the heat loss and all, this develops certain isentropic efficiencies. Okay, so for example, in this case, if you see this compressor, instead of following this path, there is some irreversibility and it ends up somewhere here. Similarly, this turbine, instead of isentropic expansion, what happens, there is certain increase in the entropy of this and it goes for some irreversible expansion. Okay, so they are, means basically because of the adiabatic heat losses, means because of some heat losses and friction available, what's happened, this instead of having isentropic compression and isentropic expansions, these compressions and expansions deviate from the isentropicness, okay, or adiabaticness. So therefore we plot these temperatures T2 dash and T4 dash. Now many of you may have a doubt, why I have made an expansion like this, why not like this? Because in irreversible process, always entropy change is more than the entropy change of a reversible process. Okay, of course the pressure is same but temperatures are actually changing here. Okay, if the pressure and temperature are same, then entropy change is same because entropy is point function. But here, because of the friction and all, what happens, physically the molecules collide with the blades and temperatures will actually increase at compressor and turbine cases. Okay, now if you see, they have given you in first case. Okay, so first case, let us see. Let us calculate T2, T3, T4 values. First of all, we know one thing, T1 into T3 is same as T2 into T4, correct? This relation holds good for Otto cycle also. So whenever, oh, some spamming is going on, good. So anyhow, leave it. So see here, T1 into T3 is equal to T2 into T4. Okay, so now if you see, initially if you don't have this, then first of all, what is the compression, this pressure ratio 5. Okay, so pressure ratio is 5, so which is RP generally. So therefore what is the thermal efficiency of Barton cycle generally? 1 minus 1 by pressure ratio power gamma minus 1 upon gamma, correct? Yes or no? This is the efficiency expression for direct efficiency if you have a compression, if you have a pressure ratio and also the ratio of specific heats, correct? So please type in the chat box, yes or no. Whenever you have a pressure ratio and also we know the ratio of specific heats, then RP whole power gamma minus 1 upon gamma is what you have here, correct? So please type in the chat box. Yes, have you seen this expression anytime? Have you seen this expression? Correct? Pressure ratio whole power gamma minus 1 upon gamma. Okay, so here we have the pressure ratio and gamma, the fluid is air because we are taking air into the picture. So gamma value is, gamma value is how much? RP is 5 and gamma is 1.4. It's a diatomic gas. So normally if you see for any atomic, for monatomic, diatomic, triatomic gases, the Cp by Cv value, this is 1 plus 2 by F actually. Okay, this F is called degrees of freedom for the molecules. Okay, which we will discuss in a detail sometime later because this is just short course. Okay, so this F for normally for this monatomic gases, F is 3. Okay, for monatomic gases we have 3 degrees of freedom, for diatomic it is 5 and for triatomic it is 6. Okay, so that's how when you put 3 here we'll get 2 by 3 is 1.67. Gamma for monatomic gases is 1.67. This degrees of freedom is 5 for this is 5 for diatomic gases, so 2 by 5 is 0.4, so 1.4 is for diatomic gases. Okay, for triatomic it is 3, so 2 by 3 is point, for triatomic it is 6 actually, for triatomic it is 6, so 2 by 6 gives you 1 by 3 and 0.33. That's how we have the specific heat ratios in this case. Clear? So anyhow, if you see this, eta 1 in the first case is 1 minus 1 by RP, 5 to the power gamma minus 1, 0.4 by 1.4. So if you do this directly, then we'll get 5 power 4 by 14, 5 power 4 by 14. Okay, 0.4 by 1.4 anyhow. So reciprocal of this and subtract this from 1. So 0.3686, correct? Did you all get 0.368? Yes, 0.3686. 0.3686. Okay, good. So this is the first case. So first case efficiency is how much? 0.3686. Good. Now what about the second case? Let us see. In second case, the compressor and turbine has got some adiabatic isentropic efficiencies. Okay, so isentropic efficiency of compressor in this case is isentropic efficiency of compressor. If you see, normally whatever the work you need in the ideal case, and that divided with the work actually you are putting in. Okay, obviously actual work you have to put will be higher, because some, in case of ideal case, what happens, this is isentropic, there is no heat interactions. Okay, so but here there is certain amount of reverse built in the system, so we write this as T2 minus T1 divided by T2 dash minus T1. Correct. Similarly, in case of isentropic efficiency of turbine, if you see in that case, T4 dash or T3 minus T4 dash divided by T3 minus T4. Okay, so this difference is larger, so T3 minus T4. These are the values that you have. Now, first of all, to get this T3 dash and T4 dash, because for calculating efficiencies we need them. Okay, so we have to identify what is T2 and T3 here. Okay, in this case, T1 is anyhow known to you, so T1 is given to you. So P1 is 100 kilopascals or 300 kilopascals something, 300 Kelvin and 1 bar, which is 100 kilopascals, and T1 is how much? T1 is 300 Kelvin. Okay, so this is 300 Kelvin. Okay, so we have 300 Kelvin. So if you, okay, let me take one slide, empty slide. Fine. Now T2, let us see, combustion ratio 5, and after heating in the combustion chamber, its temperature raised to 1000 Kelvin. So T3 is 1000. Okay, so T3 is 1000. Oh, just a minute. Fine. So T3 is 1000 Kelvin. So if you can calculate T2, then just by using this relation, you can calculate T4 easily. Okay, so how do you calculate T2? So for 1 to 2, for process 1 to 2, what we know, P1 per 1 minus gamma into T1 power gamma is equal to P2 power 1 minus gamma into T2 power gamma. Okay, so T2 is equal to T1 times of P1 by P2 whole power 1 minus gamma upon gamma. Correct. So this can be written as P2 by P1 with a minus sign change. So T2 is T1 times of P2 by P1 whole power gamma minus 1 upon gamma. Okay, because by swapping these two, you can change a minus sign. Okay, so P2 by P1, this is the pressure ratio, P2 by P1 or P3 by P4. This value is 5. Okay, so 5, T1 is 300 Kelvin into 5 power 0.4 by 1.4. Okay, so if you calculate this value, your answer is in some Kelvin. So 5 power 4 by 14. Okay, 0.4 by 1.4, this is 1.58 something multiplied by 300. So 475.145. 475.145. 475.145 Kelvin. Okay, so T1 is known, so T2, so T4. What about T4 in actual process? In ideal case, T4 is T1 into T3 by T2. This is 300 into 1000 by T2. Okay, so what about T2? 475.145. So this is in some Kelvin. Okay, so how do you get this? Reciprocal of this into 300 into 1000. Okay, so 631.385. 631.385 actually here. Okay, so 38 Kelvin. Okay, now here you might have observed one thing. Whenever I have done this TS diagram, here I have done a bit mistake actually. If you see, this T4 should be higher than this T2 actually always. Okay, so T4, here I have just done for some diagram purpose because I cannot draw it to the scale, but physically I am telling you always the exhaust gas temperatures should be higher than the temperatures after combustion. Okay, this advantage of having higher temperature we will use for calculating the, there is some concept which is called regeneration. Okay, normally in case of even in HPCL and all, when we are working, we used to do it. So what we do is, whatever the exhaust gases that are coming out of the turbine, we will pass them over a loop of the gases which are after combustion, so that some part of the heating of the gas coming out of the compressor is done with the help of this exhaust gas loop. Okay, so that we save some part of energy. Okay, and normally you see intercooling is one very good technique in case of combustion. In industries, what I have worked previously, we have seen a compressor of 18 stage intercooling, or 21 compressor is 21 stage intercooling actually. Normally we do 21 2 stage intercooling, at maximum 3 stage intercooling in books and all, but practically when you go to industries and all, there are very high stages of compression. Okay, so that's what we do. Now anyhow, this is what we have. Okay, so now if you see, therefore T2 dash is equal to T2 dash in this case is equal to T2 dash is equal to T1 plus, or first of all let us see, isentropic efficiency of compressor is equal to isentropic efficiency of compressor T2 minus T1 by T2 dash minus T1. Okay, so T2 dash is equal to T1 plus T2 minus T1 by efficiency of compressor. Okay, similarly, what about the isentropic efficiency of turbine? Isentropic efficiency of turbine is T3 minus T4 dash, T3 minus T4 dash from this equation is T3 minus isentropic efficiency times T3 minus T4. Okay, so this is what we have actually. Okay, so T3 minus this particular value, T3 minus T4. Okay, so if you perform this calculation, then T2 dash is how much? T1. So what about T1? 300 Kelvin. Okay, so 300 plus T2 minus T1. So T2 minus T1, 175.145, 175, correct? If you take 300 out, 175.145 divided by isentropic efficiency of the compressor. So compressor has this isentropic efficiency of 0.85. Normally, even in industries and all, if you see 0.88% or 0.9 around this, okay, 85 to 90% somewhere it fluctuates. Okay, so 0.85 here. Okay, here it's given how much? 0.85. Okay, 0.85. So this value is going to be 175.145, 175.145 divided with 0.85. So this value plus 300. Okay, so plus 300, 506.05, 506.05 Kelvin. Guys, please be careful when you are doing this calculation. Definitely this temperature should be higher than this temperature. It should be more than 475. Okay, if you didn't get value higher than 475, means basically the T2 in ideal case, your calculation is definitely wrong. You should go for calculation again. Okay, so because practically even means during case of friction and all, what happens, because of the increase in the entropy, the compression ends at some higher temperature than the ideal case. Okay, this is the fundamental basic behind this. So this value should turn out something more than this value. Okay, now coming to this, T4 dash is equal to T3. What about T3? 1000 minus efficiency of turbine, isentropic efficiency of turbine 0.87. So this is 0.87 times of T3 minus T4. So 1000 minus 631.38. Okay, so 631.38. So T4 dash is equal to, so if you perform this calculation, 1000 minus 631.38, 631.38, this value multiplied with 0.87, multiplied with 0.87. So subtract this from 1000 again. Okay, so subtract this value from 1000. Okay, so 679.3, 679.3 Kelvin. Okay, this also should be higher than this. Okay, so 679.3 Kelvin. These are the intermediate checks. Okay, you can check meanwhile whether your calculations are going on correct track or not. You can check using these simple concepts. Okay, so that T2 dash should be higher than T2, T4 dash should be higher than T4, these things. Okay, now if you see, in case of eta 2, net work interaction by heat supplied. Okay, so isentropic, this thermal efficiency in the second case is Cp times of actual work done by the turbine is T3 minus T4 dash, correct? Minus what is the compressor work input? T2 dash minus T1 divided with heat supplied, which is Cp times of T3 minus T2 dash. Okay, so this is what we have actually, because in actual case the work developed by the turbine is only due to this expansion 3 to 4 dash. Okay, and compressor work input is 1 to 2 dash and heat supplied is from only 2 dash to 3. Okay, so that's why we have this terms. So anyhow, Cp if we cancel out, so in this case T3 minus T4 dash, T3 1000 minus T4 dash, this guy 679.3 minus T2 dash minus T1. So T2 dash is 506 point, okay, 506.05 something, minus T1 300 Kelvin. So this divided with this value divided with T3 minus T2 dash. Okay, so T3 minus T2 dash. Okay, so minus T2 dash. So what about T2 dash? Again 506.05. So if you perform this calculation, you will get the isentropic the thermal efficiency of the cycle in the second case with this turbine and compressor having certain isentropic efficiencies. Okay, so let us perform this calculation. 1000 minus, okay, so negative of this plus 1000 plus, okay, minus 206.05. So minus 206.05. Okay, so 114 point something divided by 1000 minus 506. 1000 minus 506.05. Okay, so 0.2321. 0.2321. Okay, 0.2321 actually here. Okay, and previously what is the thermal efficiency in case 1? 0.3686. So if you calculate this value, therefore eta 2 minus eta 1 modulus divided by eta 1 into 100 is equal to how much? This is the percentage decrease in the efficiency. So if you calculate this 0.2131 minus this is how much in the first case? 0.3686. 0.3686, correct? 0.3686. Okay, 0.3686. So this value divided by 0.3686. Anyhow, we need only magnitude. So into 100. So it's almost some 37% loss. 37.03. 37.03. Almost some 37% loss in the efficiency because of some 15% of effectiveness or 15% changes in the isentropic efficiencies of the turbines and compressors. In power plant, compressor plays very important role. Okay, because the reason is the turbine blade casings and all. If you, yes, 37% is correct answer. Okay, correct result. So if you see, this compressor is one very important device because whatever the saving you can take, net effective work output, whatever you can take from the turbine or the work ratio, okay, W net out of whatever the produced by the turbine, this mainly depends upon the compressor. Okay, so compressor should be set in such a way that the intercooling stages of intercooling, that's why 18 stages, 21 stages, these are kept because work produced to the compressor should be less. Otherwise it's no point, right? You produce the turbine work, again you give it back to the compressor, then what is the point of running a cycle? Okay, your turbine keep on generating work, again your compressor keep on consuming work, then you cannot take out work effectively from the plant actually. Okay, so turbine is anyhow it's set to maximum limits till we'll stretch it till the metallurgical limits, but the compressor is played very important role. Okay, so that's why staging of the compressors and all is very important normally if you work somewhere. Okay, clear? So is this clear to all of you? So please type in the chat box, is this clear to all of you? Mahvish, sorry. So if mechanical questions, if mechanical preparation खराब हो गया है, how to prepare for XC in 0 to hero manner in remaining time? Please tell us the roadmap for XC from now. Okay, I'll tell you definitely. So first of all, I'll tell you one thing. This year number of aspirants applied for XC is around 4,500 plus. Okay, yeah, I'll tell you. I'll spend some time. Should I solve XC PYQ or Abhyas batch? Please tell us a proper way and what will be sufficient. Tell everything. Okay. So I'll tell you one thing. Every year, generally, the trend is 60% to 70% on an average. Okay, 60 to 70% of the paper is based on previous year questions and previous year models. Okay, I don't say the exact questions come, but obviously, if we can solve all the PYQs of at least 15 years, that would definitely bag you some good confidence and good enough marks for getting some 60 to 70% of the marks. Okay, and especially in, to be honest, frankly speaking, the number of candidates writing mechanical and writing XC got decreased very much, which is very unfortunate for us, but still it's good to some aspirants in some point of way. Okay, but if you see, when you get this 60 to 70% of the marks, means if you get 60 to 70 marks in gate examination in after 2021 exclusively, okay, your rank and your score is good enough to give you a PSU. Okay, but if your target is XC engineering sciences paper, definitely try to plan for more than 75 marks Okay, so if you get more than 75, your score what you get is good enough for getting admission in IIT in the core branches, means thermal design, manufacturing, okay, or some recent branches like nanotechnology, all these things. Definitely it will help you out. Okay, make sure a target of 75, and that you can easily get by writing test series and also by writing this what do you say, PYQs. Okay, so if you prepare your PYQs very much, then definitely it will be very good. How to approach such lengthy questions in exams. Look here, since my intention is to revise maximum number of points in a single question, I have intentionally kept these questions lengthy, but you have seen many of the questions in previous years and all, they are very simple. Okay, only few questions you'll have lengthy, especially when questions comes from this Rankine cycle. When they ask about a heat Rankine cycle, sometimes they don't give the Danish fraction values. Okay, so you have to calculate by using entropy equations and all. At that time it will be little lengthy. Okay, but here my questions are, means my questions in sense, I have set the questions in such a way that you will use majority of the points to solve one question. Okay, so that will be a good division. For example, tell me honestly, we have been doing for almost 2 hours. Okay, from now, I mean till now. Okay, so tell me, to solve these questions, will you need 2 hours in exam? No, no, hardly every question will be solved in 4 to 5 minutes. Okay, but what are the kind of points we have discussed here? We have discussed so many good points, correct? My intention is to touch all those good points whenever we are solving these questions. That's it. Okay, so that's why intentionally I have asked all these things. Otherwise I can give you just only calculate isentropic efficiency of compressor, these kind of questions, right? But that's not the case. Okay, fine. So shall we go for the next question? Yeah, 37.03 is correct answer. Okay, Mahvish, please go for PYQs of XE for past 15 years and also write one test says, that could be helpful. What material to solve and priority of material, please tell. At this point only, because you have only 20 days left, so go for PYQs and test says, that could be fine. Okay, because if you start reading textbooks now, that would, that won't help you out. And you can follow our Gatopedia, which is short notes, that could definitely help you. Okay, do you all know how to get the Gatopedia copy? So please type in the chat box. Do you all know how to use the short notes? Because we have put some effort on that, and we ourselves have finished that complete short notes, which is the Gatopedia for mechanical. So do you all have idea on how to get the copy and how to get the how to go through the things? Okay, yeah, if you have any doubts you can ask me. I'll show you how to make use of that book. Actually, it's a very good book. It has all the formulas, key points, okay, all the things whatever you have. Okay, so that will be helpful. Abhyas batch we can look, yes sir, to get under 100 and save my year. Yeah, you can always solve Abhyas batch, because there we have solved again some good questions. Okay, again like revision kind of thing, so it would be helpful. Okay, and my suggestion to you is, if possible, on this channel we have this one shot says. Okay, so you can go for that one shot says, which saves you a lot of time, and also that can give you the best results, best possible results, because at this point to search 2-3 books and make some good notes is very difficult. Okay, because you have very short time. Now what you do is, you generally at this time you follow the one shot says that are on this channel. That will be definitely helpful to you. Okay, you have the one shot says on this channel, you can just view it. Okay, so that will be very much helpful to you. Clear? Fine. So let's go for the next question quickly. Sorry. An engine working on Otto cycle has a combustion ratio of 6:1. If the specific heat at constant volume increases by 1%, then the magnitude of percentage change in thermal efficiency is dash. Okay, so if specific heat at constant volume changes by 1%, what would be the change in thermal efficiency? So please try to solve this. It's a good question, right? First of all, if you understand physically, what happens if specific heat changes? Okay, so if specific heat changes, then what happens? Why thermal efficiency will change? If specific heat is increased, then what happens to thermal efficiency? Will it increase or decrease? Will it increase or decrease? Okay, fine. Let us do some mathematical analysis, then you will understand this. Okay, so see, first of all, So if you see, thermal efficiency of Otto cycle is 1 minus 1 by R power gamma minus 1. Correct? We have this. So R is the combustion ratio and gamma is the specific heat ratio of the substance. Okay. So in engine working on Otto cycle. So let us take A is the substance. Okay. A standard Otto cycle. For example, let us say this is A standard Otto cycle. Cold A standard Otto cycle has a combustion ratio of 6:1. If the specific heated constant volume increases by 1%, then the magnitude of percentage change in thermal efficiency is dash. So this we can write as, here the main point of interest is this specific heated constant volume CV. So what about CV? CV can be written as R by gamma minus 1. So this gamma minus 1 can be written as R by CV. Okay. And once you fix the substance, then characteristic gas constant is fixed, correct? Because universal gas constant doesn't change, molecular weight of the substance doesn't change. Okay. So let us see. Gamma minus 1 is equal to R by CV. So this implies thermal efficiency is equal to 1 by R to the power minus R by CV. Okay. Gamma minus 1 is R by CV. So this is R to the power minus, okay, we don't have a minus sign here. So R to the power capital R by CV. Okay. So this is what we have. This can be written as, sorry, okay, fine. So this can be written as 1 minus small r to the power capital R by CV. Okay, we can put a minus sign here. So this is the relation. So if you want to find for change in CV, what is the change in thermal efficiency, then let us go for the differentiation. But let us use some mathematical things to simplify the differentiation. What we can do is 1 minus eta is equal to R power minus R by CV, and if you apply log 1 minus eta, ln 1 minus eta is equal to minus R by CV into ln R. Okay, so because it is easy to differentiate in this form. Okay, so minus R by CV into ln R, because if you directly want to differentiate this, it will be a little complicated, e power minus 1 by x differentiation and all. So let us talk about this. So now differentiating both sides, okay, let us not differentiate with respect to any variable, let us just differentiate. Then differentiation of log 1 minus eta with respect to eta is 1 by 1 minus eta into d eta is equal to, this R is constant and combustion ratio of the engine is also constant, so minus R times of ln R into this CV. Differentiation of CV is minus 1 by CV square into dCV. Okay, so we have this. So this is the expression. So minus of minus gets cancelled, minus of this minus gets cancelled. Now we can write one thing, 1 by or d eta upon 1 minus eta is equal to, now this can be written as R times of this ln R is anyhow constant, this R by CV, we can write something here. Okay, so R can be written as CV times of gamma minus 1 into ln R by CV square. Okay, so this is CV square into d times of CV. Okay, so this is d times of CV here. So CV and this gets cancelled, so we can see d eta by 1 minus eta is equal to gamma minus 1 times of ln R into dCV by CV. Okay, so this is what we have. Now let us do one thing, you multiply an eta here and also here. Okay, so thermal efficiency, let us multiply here, and this gives you d eta by eta, because we want percentage change, correct, is the percentage change in thermal efficiency. So this is a fractional change, so if you multiply by 100 we'll get change. So 1 minus eta by eta into gamma minus 1 into ln R into dCV by CV. Okay, so this is what we have. So first of all, let us calculate what is eta value at this condition. At R is equal to, what is the combustion ratio they have given you? At R is equal to 6 at this particular condition, and gamma is 1.4 in have a standard cycle. So thermal efficiency is 1 minus 1 by R power gamma minus 1. Okay, R power gamma minus 1. So 1 minus 1 by 6 power 1.4 minus 1, which is 0.4. So the thermal efficiency in this case at this particular condition is how much? 1 minus 1 by 6 power 0.4. So 6 to the power 0.4. Okay, so 6 to the power 0.4, reciprocate this and subtract this from 1. 0.5116. 0.5116. So let us substitute in this relation. It is given CV changes by 1%, correct? The magnitude of percentage, okay. Specific heat at constant volume increases by 1%. Okay, so let us suppose if you multiply 100 on both sides, if you multiply 100 on both sides, if you multiply 100 on both sides, then this is percentage change. This value which is here, the percentage increase is given 1 unit. Okay, so this quantity is 1, it is 1%. Okay, so this is 1%. So let us keep eta and gamma value known to you, R is known to you. So let us keep all these values. So if you keep percentage change in thermal efficiency is equal to d eta by eta into 100 is equal to 1 minus eta by eta. So eta value is this. So let us store this value. Okay, so this is the thermal efficiency. So 1 minus eta divided by eta again. So 0.95 this value into gamma minus 1. So into 0.4 into ln R. So R value is 6. So ln 6. So into ln 6. Okay, so this is the value 0.684 into 1 actually. Okay, so this is 0.684 actually here. So this value is actually positive, correct? 0.511 is thermal efficiency. Yes. So this is thermal efficiency. Okay, and if this is thermal efficiency, then this is the percentage change in the thermal efficiency of this cycle basically. Okay, so d eta by eta is actually into 100 is 0.684 actually. Okay, into 100 is what we have taken, right? It is 1. Okay, so 0.684%. Right? So please type in the chat box. Is this clear? Yes or no? So type in the chat box. Is this clear to all of you? Look, here I want to tell you one thing. Normally we assume Cp and Cv values constant, correct? Within this temperature range, okay, of these cycles. The reason is this. You might have understood. Okay. Normally for some compression ratios, when Cp Cv changes by 1%, this is in percentage. Okay. So it is less than 1%. Okay. So that's why the changes in Cp and Cv are not much taken into the picture whenever you are dealing with cycles. Okay, Amit, Sukumar, Pradeep, Punnab, Asif, all of you. Okay, fine. So shall we go for one more question? So please type in the chat box. Shall we go for one more question? Okay. Are you all liking the questions? Yeah. Okay. Good. So let's go for one more question. Okay. Some big question is there. Fine. Let us see what is this big question. Consider a gas turbine power plant operates on a simple Brayton cycle. Okay. Between the pressure limits 100 kilopascals and 700 kilopascals. So pressure ratio is 7. Air enters into the compressor at 30 degrees Celsius with a weight of 12.6 kg per second and leaves at 260 degrees Celsius. Okay, so air leaves the compressor at 260 degrees Celsius. Now this air and diesel fuel with an air fuel ratio of 60 are burned in the combustion chamber with a combustion efficiency of 97%. Okay, so we have some combustion efficiency of 97% because what happens generally, whatever the heat that is liberated, all heat won't be with the system. There is some loss. Okay, so there is some combustion efficiency, or sometimes what happens, some part of the fuel remains unburnt. All these things will happen. Okay, then diesel has the heating value, calorific value of 42,000 kilojoule per kg. Combustion gases leave the combustion chamber and enters the turbine whose isentropic efficiency is 85%. Treat the combustion gases as air with Cp is 1.093, okay, kilojoule per kg Kelvin. Cv is 0.806 kilojoule per kg Kelvin and gamma is 1.357. the back work ratio will be dash. Okay, so first of all, tell me, some options are also given. Good. What is back work ratio? So please tell me, what is back work ratio? The previously what I'm talking about. Okay, so what out of the turbine generated work, what part is actually consumed by the compressor? Okay, so that's what it's called back work ratio, and your job as an engineer is to minimize this back work ratio. Otherwise, what happens? Whatever your turbine produces, same will be going to the compressor again. Okay, so it will be difficult. So let us see. They're asking about back work ratio. Back work ratio. Okay, so which is work of compressor by turbine. Okay, compressor work divided by the turbine. Yes, of course, compressor work divided by the turbine work. The name itself tells out of generated work by the turbine, what portion is actually taken back, okay, by the compressor. That's called the back work ratio basically. Okay, now let us see this back work ratio. So first of all, let us try to construct this cycle. Okay, so if you try to construct this cycle, T S, then let us suppose if you take some pressures about which it is operating. So this is high pressure or P pressure of this combustion chamber, and this is pressure of the exit. Okay, so pressure of the exit, for example. Then in that case, you have some compression. Then there is some heat addition at constant pressure. Then there is some isentropic rejection, obviously. Okay, and again there is some heat ejection like this. There is some amount of heat ejection. Okay, so 1, 2, 3, 4. Now this is constant pressure, of course, and this is also at constant pressure. And these are isentropic conditions. This expansion is also isentropic, but this time the turbine has got some isentropic efficiency. So whenever turbine got some isentropic efficiency, the state of the turbine will be something different, 4 dash. Okay, now let us see what they are given you. Let us read the question. Between the pressure limits 100 kilopascals and 700 kilopascals, so pressure ratio is 7 actually. Okay, so anyhow P1 and P4 are 100 kilopascals, and P2 and P3 are 700 kilopascals. Okay, so this is 700 kilopascals. So whenever this, okay, I think we have pressed some button, so fine. So good, this is 700 kilopascals. Okay, so if these are 700 kilopascals, then A enters the compressor at 30 degrees Celsius. So what is T1? T1 is 30 degrees Celsius. So 273 plus 30, which is 303 Kelvin. Okay, then mass flow rate is 12.6 kgs per second. Okay, so with mass flow rate of air, m dot A is 12.6 kgs per second. M dot A is 12.6 kg per second. Okay, so this is 12.6 kgs per second and leaves the compressor at 260 degrees Celsius. Okay, so what is T2? 260 degrees Celsius. The meaning of this is 273. If you do 273 533 Kelvin. Okay, so this is 533 Kelvin. Now this air and diesel fuel with an air fuel ratio of 60 are burned in the combustion chamber. Okay, so what is air fuel ratio? M dot air by m dot fuel is how much? 60. Correct? They have given 1:60 is the air fuel ratio. So if mass of air to the mass of fuel is 60, then in that case mass flow rate of fuel is how much? Mass flow rate of air, which is 12.6 by 60 actually, which is 0.21. Correct? Because 6 cancel this 2.1 times, so 0.21 kgs per second is the fuel flow rate into this combustion chamber. Okay, so therefore now what is this heat added? Heat added is Q3 minus 2. Okay, so heat added, Q added is equal to mass of fuel, mass flow rate of fuel into calorific value. Okay, so into or heat value, let us say heating value, into, now this combustion chamber has got some efficiency. Okay, so whatever the heat that is generated, completely the fuel is not burnt. Okay, so the combustion chamber has got some efficiency. So efficiency of combustion chamber, efficiency of combustion chamber. Okay, so what is mass flow rate here? Mass flow rate of fuel is 0.21 into, what is the heating value? Heating value means basically the calorific value is 42,000 kilojoule per kg, 42,000 kilojoule per kg, and combustion efficiency is how much? Combustion efficiency is 97%, so 0.97. So these many kilowatts is generated as power. This much amount of heat is actually supplied, correct? So 0.21 into 42,000, 0.21 into 42,000 into 0.97. Okay, so 8 table 5.4, 8 table 5.4. Okay, so this is what you have. Now if this is the case, then what about T3? This amount of heat what is supplied is nothing but the heat change in this process. So therefore this implies 8 table 5.4 is equal to mass flow rate of complete substance. Okay, air plus fuel into Cp into T3 minus T2, correct? So let us calculate this value. 8 table 5.4, this is in kilowatts. Mass of air plus mass of fuel, air is 12.6 and fuel is 0.21, so 12.81 is the total mass that is sitting here. So 12.81 into Cp is asked to be taken 1.093, 1.093 into T3 minus T2. So what about T3 minus T2? T3 is not known to you, T2 is known to you. Okay, 533. So T3 minus 533. Okay, so this gives you T3 value. Okay, so T3 in some Kelvin. Look, this is in kilowatts, so we have substituted this in kilojoule per kg Kelvin. Okay, so if you calculate this value, 8 table 5.4 divided with 12.81, 12.81 into 1.093, 1.093. Okay, 1.093. So 611.04. So T3 minus this value is 611. So plus 533 gives you 1144.04, 1144.04 Kelvin. So this is the temperature after the combustion. Yes, 8 table 5.4, correct? 8 table 5.4 is the heat which is added, and that gives you a temperature rise of the mixture to 1144.04 Kelvin. Okay, so the final or the maximum temperature of the Breton cycle at this location is 1144.04 Kelvin. Okay, now if you see this, now what they're asking you finally, they're asking you for the, okay, they're asking you for something. What they're asking you, combustion gases leave the back work ratio. Okay, so back work ratio. So for calculating back work ratio, work given to the compressor, Cp times T2 minus T1, T1, T2 are known to you, Cp times T3 minus T4. Okay, so T3 we have just calculated, T3 we have just calculated. Now how to calculate T4 actual? Okay, so how to calculate T4 actual? Isentropic efficiency of the turbine is given, which is T3 minus T4 dash by T3 minus T4, correct? So what is T4 actually? Ideally if we calculate, ideally means if the expansion is isentropic, this gives you P3 power 1 minus gamma into T3 power gamma is equal to P4 power 1 minus gamma into T4 power gamma. So this gives you T4 is equal to T3 times of P3 or P4 by P3 whole power gamma minus 1 upon gamma, gamma minus 1 upon gamma. Okay, so this is what you have, because P3 by P4 1 minus gamma is there, so if you swap those two, P4 by P3 gamma minus 1 is what you have. So ideally T4 value is how much? This P4 by P3 is 1 by 7. Okay, so this value is 7 because the pressure operating range is 100 kilopascals to 700 kilopascals. Okay, so this is 1 by 7. So T3 into 0.4 by 1.4. So 1 by 7. So this value T3 multiplied with 1 by 7, 1 by 7 whole power 0.4 by 1.4. So 0.4 0.4 by 1.4. Okay, this brackets has to be used carefully. So 656.13, 656.123 Kelvin. Okay, so this is actual T4, means ideal T4 in case of ideal expansion. But here the turbine has got some isentropic efficiency, so therefore this value of T4 dash is T3 minus isentropic efficiency of the turbine times T3 minus T4. Okay, so this gives you T4 dash is equal to T3, which is 1144.04 minus isentropic efficiency of the turbine. In this case is how much? Isentropic efficiency of the turbine is 85%. Okay, so 0.85 into T3 minus T4. So T3 minus T4, 656.123. So this is what you have. So T4 dash from this case is equal to, so let us calculate that value. 656, subtract that from 11 point, subtract this from 1144.04, so multiplied with 0.85. So subtract this value from 1144, so subtract this value from 1144.04. okay, so 729.31 Kelvin. This is 729.31 Kelvin. Okay, so 729.31 Kelvin. So therefore your back work ratio is equal to, so if you see we need these values, this is T4 dash actually, okay, because the turbine has got some isentropic efficiency. So T2 minus T1 by T3 minus T4 dash. Okay, so this is 533. So T2 is how much? 533 minus T1. Okay, so T1 is how much is T1? Did they give you? Yes, 303 Kelvin. Okay, so this is 303 divided by T3, which is 1144.04 minus T4 dash 729.31 is what you have here. Okay, so back work ratio in this case is, so this calculation whatever you get, that's the correct answer. Okay, so 729.31 correct. So 656, 729.31 correct. Our values are matching. So let us calculate this. 533 minus 303 divided by 1144.04, 1144.04 minus 729.31, 729.31. okay, so 0.5545, 0.554. so this is the back work ratio that's present here. Okay, so means you can see almost 55% of the turbine work is being consumed by compressor. Okay, so it's which is a big loss. But in case of Rankine cycles and all, what happens? In case of Rankine cycles, pump consumes very less part of the work. But practically putting a hydraulic, what do you say, hydroelectric power plant is actually very you need a lot of accessories and requirements. But for putting a gas turbine power plant, it's very simple. Only thing you have to look is fuel. But this 55%, you can see clearly the values, and these are the normal range of values. Okay, combustion chamber efficiencies and all will be around 95% also. So if you see around 0.55, 55% of the work which is generated by the turbine is used by the compressor in this case. Okay, so normally in cycles and all, what's happened is 40% to 45%. This is what it happens. But here you can see since turbine work got reduced, this is what you have. Clear? So please type in the chat box, is this clear to you? Okay, fine. Okay, so good. So with this I would like to conclude this lecture. Okay, so because we it's almost 2.5 hours, so we will conclude this lecture here and we will meet again for some time. Hopefully day after tomorrow, I think this super 30 questions, myself and my colleague Amit Moya sir will solve FM plus hydraulic machines. Okay, super 30 questions, then we will meet again for some long time. Okay, anyhow, this is for applied thermodynamics, and then we will meet for fluid mechanics plus hydraulic machines. Okay, then we will solve some good questions of fluid. Many of you might have gone through my Abhyas series, then you'll get that questions again. Okay, not that questions, I mean some other questions, but you'll enjoy the questions, will be of same level almost. Okay, So I think we have few more questions, but since we are running short of time, then we will come back. So again, so with this we have reached till this particular point of the schedule. I have completed till this particular part. So these 5 sessions were done actually. Then we have the remaining sessions. So next session tomorrow at again 4 p.m. by Ramanand Bansal sir. He will be taking on machine design again. Then we have one very interesting, some relaxing session, aptitude by one of the good faculties, aptitude by Amulyatan sir. Then again Amit Dixit sir, one of the best in the GATE domain for teaching industrial engineering and operations research. So that will be dealt by Amit Dixit sir. Himself is also a All India rank 1. And then theory of machines and vibrations by Vishwajit sir again on these particular dates. Okay, so Sunday January 22nd and January 22nd, these 2 sessions will go on 2 to 4, and again this is from 4 to the session later. Okay, so manufacturing process 2 we have finished already 1 by Swadesh sir. So 2 metal cutting and all will be taken by Aditya Paul sir, and fluid mechanics plus turbo machines I think Amit Moya sir is taking that. So please don't miss any of these sessions. Okay, similarly Apoop sir for strength of materials and Sandeep sir for heat transfer. Okay, so if you follow these things, definitely, like for example in today's class you have got some good idea on all the remaining things. Okay, look, there are some standard things which comes out. Okay, like for example for maximum work output, what is the compression ratio, what is the pressure ratio for maximum work output, all these things are commonly, and you might have known these formulas for many times. Okay, so that's why I didn't keep things on them. I have kept you some detailed questions on other things actually. Okay, clear? So please type in the chat box, is this clear to all of you? How many of you liked the session? How many of you liked the questions actually? Okay, session means not hitting the like button, I mean practically. How many of you liked the questions and all that we solved here? Okay, we have tried to touch up all the things, but anyhow I understand it's a short session for only 2.5 hours time. So there's certain obviously cannot touch 100% of the concepts that are involved, but I tried my best to put up some good questions for you. Okay, clear? So anyhow, this is our team. So as I have shown you in the beginning, okay, so we have again a very good mix of industry plus academic team actually. Okay, so people who have worked for some good time in industries and also teaching for some quite long time, like Swadesh for example 23 years. Okay, and on an average some 10 years plus teaching experience. I think I'm the youngest of the team, but anyhow good. I hope you're getting the things. Okay, so fine, then that's all from my side. So thank you all. If you have any doubts regarding anything or anything about the upcoming GATE examination or anything, you can always ask me. Okay, and we'll also meet again on 18th, hopefully the day after tomorrow, for fluid mechanics super 30 questions. Okay, I'll take fluid mechanics and hydraulic machines along with Amit Moya sir. Okay, fine then. So shall we wind up the session? Yeah, thank you all for your patience, and yeah, thank you. If you have anything to ask, you can ask me. Okay, anything to say, you can type here in the chat box. If you feel that I can help you out in something, you can ask me. So ATD कैसा होता है XC पेपर में? Very easy actually. Okay, honestly speaking, applied thermodynamics syllabus for XC is very less. For example, if you take the concepts of regeneration, reheating, all these things, they are not in the XC syllabus. Okay, like you can check easily. Okay, these concepts of reheating, regeneration, or canonizing the cycles, all these are in mechanical, but in XC your syllabus is very simple for applications part. Not formula based questions directly, but conceptually very simple questions. Okay, yeah, sometimes even if you know the formulas, you can solve the questions from applied thermodynamics, but very few questions, normally not in air conditioning and Rankines. Okay, Rankine you can do, but Breton cycles and these things you need little concepts. Okay, can you please define XC syllabus once please? Yeah, sure, definitely, why not. Let us take one website, official website, then you take to papers and syllabus, You hit on the syllabus, then go to XC, engineering sciences. Okay, so you go to engineering sciences paper. Where is it? Engineering sciences. XC should be there, right? XC, yeah. Engineering sciences. Then the syllabus is this basically. Okay, I'm showing you. Basically, syllabus between mechanical and XC. Basic thermodynamics is very, basic thermodynamics is very in depth, but applications of thermodynamics is very less for XC actually. Okay, but the main essence of applied thermodynamics you will find in if you are at ESC, prelims and mains, of course. Okay, these kind of questions, combustion chamber efficiencies, all these things will come. Class notes you will find in the link. Okay, so below this you will find a link where we will upload the class notes and you can find it from there. Okay, so coming to XC syllabus and thermodynamics, so XCE. So this is the syllabus. So here if you see, okay, all this is basic thermodynamics syllabus, but once you come to here, so thermodynamic cycles is what you have here. So see, complete ATD in one single 2 chapters actually. Okay, so thermodynamics cycles, Carnot vapor cycle, ideal Rankine cycle, reheat cycle. You don't have regeneration cycle here, but in mechanical you have. Okay, A standard Otto cycle, diesel cycle. You don't have dual cycle, but in mechanical you have A standard Breton cycle, but you don't have the concepts of regeneration, reheating and all, but there you have VCRS, vapor combustion refrigeration system or cycle is what you have here. Okay, you don't have any this only VCRS, you have simple VCRS. Okay, and coming to ideal gas mixtures, here you have some specific and L2 humidities, dew point and wet bulb temperatures, adiabatic saturation and psychometric chart. Okay, this is the common syllabus like between mechanical and XC, but in terms of power cycles you see a lot of difference. Okay, there is no concepts of regeneration or anything in XC syllabus. Okay, so from where to practice questions of extra topics of XCB, extra questions. You can solve unsolved questions of Frank and White and Single. Okay, these two could definitely help you. Frank and White will definitely help you to a very good extent. Okay, unsolved questions of Frank and White. Okay, for a few questions, for the even number questions, you have the key at the end, so you can cross check your answers. Okay, fine. So I think things are fine then. Okay, so we'll meet again on 18th for solving some super 30 questions on fluid mechanics and hydraulic machines. Okay, yeah, extra topics means which are not in mechanical, you can find in Frank and White. Okay, same thing. Fine then, thank you all. Okay, we'll meet again soon on this channel. Okay, thank you all, bye, take care. I wish you all the best for your GATE 2023. Okay, so thank you all. Thank you. We'll meet again soon. Thank you all. And then thank you.